In this lesson we want to talk about what databases are all about. There's a number of different kinds of databases, but we're going to concentrate on relational databases here as the most important ones. There's also hierarchical databases, which mostly feature in the mainframe computing area. And there's object relational and object-oriented databases who use object-oriented concepts as you have in C++, .NET, Java, the likes, to model a database. They are by no means required to use with these languages and actually are very little used yet. So relational databases really remain at the heart of database technologies. So here we see an entity relationship diagram of a database, of a relational database. And by the way, I'm using MySQL Workbench as a tool here, which is a free tool you can download from the MySQL website. You find similar tools, graphical tools and query tools in all common database systems these days. Microsoft Access, for example, had similar things for well over 20 years. SQL Server had them for a long while, and even in Oracle you find them these days. So what we see on this diagram here are the two main elements of a relational databases: tables and their relations. That's why it's called a relational database. The tables are these boxes here, like the person table for example, and the relations are these connecting lines between the tables. Let's look at the tables first. You see we have 6 of these tables here, and each table has a set of columns. In the person table we have an unique ID for each person. We have a first name, a last name, a date of birth, a manager ID, that is the person that person is reporting to, which of course is a person in its own right. We got an area to record notes, and finally we have a timestamp when that record was created. If I head over to this side, that's where it's wrong. So if I head over to our SQL editor, I can actually have a look at that table and its content. So there you see our columns that we've just looked at and we've just talked about, and then of course you see the multiple records in that table, the different rows, each row being one person with their respective details. I should remark here that there are these null areas, in particular in the nodes. That is perfectly normal because obviously you have optional elements in such a database table, optional information that you may have or you may not have. Heading back to our diagram, we want to look at the relationship aspect now, and I'm gonna take as an example this relationship between person and contact. Now for the context, this database is about persons being part of a project team with contact details, with association to projects and the likes. And we want to look here at the relationship between the person and the contact table. Now the contact table allows you to record contact details of a person, which obviously are multiple. So a person might have a telephone number or even multiple telephone numbers, might have a address, a postal address, an email address, and so on. The kinds of contacts you can actually set up in this contact type table. You see here at the end of this relationship line this split up, which indicates that is a 1 to n relationship. So in this occasion that means one person can have n records, associated records in the contact table. That allows to nicely structure your data and avoid redundancies. if you think about that scenario of a person and multiple contract details, say in an Excel sheet, you would obviously create a lot of redundancies, and it would look kind of like what I can see here in that second query, where actually I've pulled together the various data from the various related tables. We obviously learn at a different point how to exactly do that, but you can see nicely now there is multiple lines for each person depending on how many contact details they have. And you see Paul Miller, for example, has 3 records here: an email, a phone and address. So what you see is obviously in this output his personal details are redundant, and that is, if it was like that in your data source, not a good thing to do, because once you need to maintain this data, you will probably create problems there. Right, so that way having a relational database allows us to reduce redundancies, but of course in the end we need to create such flat views for many usages. So that's kind of our overview about relational databases, what it's all about. And obviously there's lots and lots of detail aspects in all the different areas which will be subject of separate lessons. So that's us at the end of our overview to what databases are all about, in particular relational databases. And obviously there's much more to say about tables and relationships and querying the data we hold in our database, which of course is subject to a whole range of further lessons. In this lesson I want to talk about the role of databases in application development, or maybe the other way around, the role of application development to make databases useful. As you can imagine, if you look at such a database schema with all the nicely structured and designed tables, it's a great way of storing your data in a very efficient way, but it's not a particular easy and beautiful way to actually look at these data and work with these data, input data and so on. If I have a quick look on my SQL editor, again here I see one such table, the person table, and of course I see I only have the data of that person. What I kind of need typically will be some kind of view like the person contacts that I've prepared here, which shows me, for example, in this occasion, the users with their contact details and the kind of contact details. So we have our different people in the team, and here we have again Paul Miller with his 3 different ways of contacting him. It needs quite a complex query to get these data together, and we'll learn, of course, at a later stage how to do that. But it proves the point that actually it is not very easy to work for an end user. So what we're going to do is we're going to have, of course, front-end applications that will make use of this database and do all the visualization and build proper interfaces for the user to display data, to input data and so on. And I'm going to show you a very simple example here, taken from PHP, being obviously one of the most common application development languages in web application development, maybe aside from .NET, and of course Java is another important one. So if I have a look over here, you see there I've in a very simple way plotted out this database table on a web page screen using PHP. So how do we do this? If I look at the PHP script behind there, you can see the idea of these application modules that do this. It is reasonably similar whether you use PHP or Java, .NET, whatsoever. The concept is always about the same. You need to establish a connection to the database server and to the database you're interested in. Typically that needs some kind of user and password, as we have here, and because it's a SQL server and it's a local SQL server, I'm just using the default user and password. In a productive environment, of course, you want to add a bit sensible security to that setup and not use the default user and the default password. That would be relatively easy to hack in, of course. Right, so you see in the first instance we have one PHP comment that does the database connection using the server, the user and the password, and once that connection is established, it uses the database name to connect to the individual database in the database server. Next of all, we construct our query, which of course here is the simplest of the simplest, a simple select star from person, which means we want to plot out the whole table. Not something you will do in practice very often. Typically you will filter your data, but of course that's all things we learn individually. Here we just want to see the concept of application development. Next we can execute this query against that database connection we've set up before, and that will return us what's called a record set. A record set includes that list of records that are query returns. So what we've just seen on the SQL query tool and also seen on the web screen, the list of our records as they are in our database. Well, if that has worked fine, of course something could have gone wrong. The database connection could have had a problem, your query could have an error in it, and so on. Once it's gone wrong, we can simply output these data. I'm going to scroll that a bit so we see that aspect. And you see that's nothing than a normal HTML table which we construct step by step, put our headers in, and run a loop over our record set to fetch the individual records. Here I've used the object style. There's also an array style, whatever you find more suitable. And you see all I'm doing here now in this section is I'm plotting our individual content in each column of the record on the screen. And you see the name of each of these elements in our record set object is simply the name of the column. Well, and finally I do a bit of cleaning up. I destroy the record set, I close the connection, and that's me done. And the result of running that script is this output on the screen. That is, as said, of course, a super simple, basic, easy version of doing that. And in real terms, of course, you will add all kind of design to it. You want to look it nice and neat. You will add forms to it to modify content, to enter new persons, and so on and so on. There is no limits to your creativity. But what we've seen on this example is that it's pretty simple to integrate such a database into your web application scripts. Once the database is created, once the database is populated with data, it takes only a few lines of code to actually build that wrapper around. So really the important part is to design the database and to understand how to query the database, that we get the right data on the screen, because the last thing you want to do is pushing all kind of data over the network and then dissect them within your PHP script, when actually the database could do that for you. And that's of course the whole purpose of SQL querying. And so obviously we will spend lots and lots of lessons here to actually learn about all these different options of SQL querying. In this lesson we now want to take a closer look at database tables and database relationships. So here we have our database schema, our database diagram, or entity relationship diagram as it's sometimes called. And obviously our boxes are the tables and the lines between them are the relationships. This database is all about persons that are involved in projects, with their role in the project and with their contact details like telephone numbers, email addresses and so on. Let's have a look at one table. This person table has a couple of entities, columns in itself, and of course we have a unique ID for the person to identify clearly. We have a first name and a last name, date of birth, manager ID, they reporting to a field for notes about that person, and a timestamp when that person was created in the database. So each of these columns has a clear name, has a unique name within the table, which is important because obviously that is how we are going to access the data in that particular column of a particular record. Next to it you can see that each column also has a data type assigned. Starting on the ID we have an integer. Primary keys or unique IDs in records should always be numbers because it's the easiest for the database to handle, to sort, to search on and so on. Then we have our first name and last name, which is a variable character, which means it is a field that can vary in length and the database will just optimize the storage for it. And I've used the default of 255 characters here, which is the kind of old-fashioned default, but it does the trick for a lot of things. It's worthwhile noting here that there's no much point being much more distinct, because the whole idea of a varchar is that the database uses as much space as you actually put as content in there. So if your first name is only 5 characters long, it will only use actual 5 characters of memory for that. That's why I prefer to just use these kind of default lengths for it, because that way you don't get in trouble. There's a lot of databases around that are very finely designed on how many characters you have for a first name or a last name, and if you come around in the world you very quickly find out that standards are extremely varying. In many European countries you get very long last names, combined last names for example. In some countries you get very lengthy first names, so you really don't want to delimit that to 10 or 20 characters because you will easily run out of space there. Then we see we have a column with a type date here. Obviously your date of birth is a date typed field. Again we have a manager ID, which is effectively the ID of another person. And we have something called text, which is a large area, which can take much more characters than a varchar could do. And again, finally for the created we have a timestamp. If you look around on this schema, there's a few other bits featuring. In particular over here we have a double, which is for floating point numbers. as you would expect for a project budget, as this column is about. So you see, each column in such a database table has a name, has a data type and a size for the data type if that is appropriate, and finally it has something that is here expressed by the solid or by the hollow diamond, the ability for that particular field to be null or not null, which basically means do you have to have a value in it, or is it an optional column? And finally we have here the keys, and we're going to look at the different kind of keys separately in another lesson in more detail. Here all we need to know is that's the primary key, which means that is the column which makes sure that every single person can be identified uniquely. Right, let's take a look at the relationships. If you look at these lines, you see they all have at one end that splitted end, which points to them being a 1-to-n relationship. Which means one person, for example, can have n contact details, or one person can have multiple assignments to a project. One project can have multiple persons assigned. One role can have multiple persons, obviously. If, say, you have a development team, that you likely have more than one developer in that team. So that way you express these relationships and structure your data into the different tables. And that's really what the core principle of relational databases is. Whenever you have multitudes of something, you will outsource this into an external table and create such a 1-to-n relationship. Learning that is a skill in its own right, and database design is an issue and a subject in its own right, which we're not gonna go into here in detail, but it's important to understand these relationships. There is also one-to-one relationships, though in reality they hardly occur anymore. They used to be used in historical systems when you had significantly less front-end applications and you would actually have end users querying a database directly, and all you could do is restrict access on a per table basis. A typical example in those times was to separate personal details into the different departments. So you would have a table with personal details that everyone can see, and you would have a table with personal details for the same set of persons that, for example, only the HR department would be allowed to see. Say, for example, salary details. In modern database systems, you really don't need this kind of structure anymore, because typically you will organize these through dedicated front-end applications that show the right data that the right audience is supposed to see, or you can set access limitations on a per column basis rather than only on a per table basis. So it's good to know that there is one-to-one relationships in case you see them in a legacy system, but you wouldn't really design them in a new database systems nowadays. The other important relationship type is the M2N relationship. And the M2N relationship, though a theoretical construct that expresses that one entity not only has n related entities on the other side, but the same goes the opposite around, is a theoretical important construct, but it's actually solved in a very easy way in databases by a combination of two 1-to-n relationships with a intermediate table in the middle. And an example is this section here. So you see we have the person table, we have the contact type table, and we have the contact table. So in the end what we are expressing here is that one person can have multiple contacts, but also can have of course multiple contact types, and equally multiple each contact type of course has multiple persons assigned to it. So just the same as a person typically will have an email address, a physical address, a telephone number, and so on. Of course, to each contact type, like for example an email address, there is of course multiple people who have an email address in this world. And that's these kind of typical situations where a one-to-n relationship alone wouldn't help you. So you need the m-to-n, which you split up by putting this middle table in. So in the end, this middle table does nothing else but pairing up your m and n partners. So as you can see in this table, it has nicely highlighted at this moment two key tables, which is basically the combination of the primary keys of both tables. So you have any possible combination between a contact type and a person. And then you have on this occasion that value field where you can add the exact content of that contact type. So you would have, for example, for the first person, the contact type telephone, and then the value field would hold the telephone number. For the second contact type, say an email address, the value field would keep the email address as a text. So that way you resolve these limitations that a one-to-n relationship would give you. And that is indeed a very common scenario. Once you start creating a database, you very often find, once you think about a one-to-n relationship, that you say, yeah, actually thinking about it, it is an m-to-m relationship. And you can test this concept further, and that's done here in that project person table. The m-to-n can actually be something with more than two tables, which makes it an m-to-n to o to p to q to whatever far you want to go. And I've certainly often enough seen these kind of m-to-n relationships that actually at least use 3 or 4 tables, and occasionally I've seen much bigger. But you see, the concept is the same again. You have that middle table, and on this occasion this middle table is really just a linking table, which gives you the combinations of, on this occasion, person, project, and role. So what you basically express here is to say a particular person is part of a project, and in that project has the role. So for example, Peter Miller is part of the web design project and is a project manager in that project. So this kind of structure gives you an extremely powerful way of structuring your database and structuring your data. Because as you can probably imagine here, this m-to-n relationship construct allows you to record as many combinations, as many associations as you want in your database. There is no limit whatsoever except for the database size limit, and these are well out of reach nowadays. So whatever kind of teams you have, in whatever composition, you could actually keep the data of such a team in this reasonably simple database structure. So here we've seen in some more detail the whole concept of tables and relationships between them, and a few typical relationship types, and of course That is the backbone of every database system, which then we use to query the data to get the information together that we actually want to know on this data. In this lesson we now want to talk about database constraints, that is primary keys, foreign keys, unique keys, and there's also a couple of other constraints that you can set up in a relational database. We want to look at what role they play, why they are important, and how you work with them. We've mentioned elsewhere already that we have these relations that constitute a major element of relational databases, of course, because that's why they're called relational databases, because you have tables that are linked by relations, like this one-to-n relationship here. How is this relationship built up? By default, SQL and a lot of the older database systems don't have any real enforced technical structure for it. So the trick to create a relationship is by having primary keys and foreign keys. You see here in the person table as well as in the contact table that there are these fields that have this wee key on the left. So that is your keys, and depending which side of the relationship you are, we're talking about a primary key or a foreign key. So the primary key, first of all, always sits on the one side of the relationship. So each person has a primary key, which is that unique ID, which ensures that every record in that table can be identified uniquely. It is good practice to use numeric values for that, simply because a database can handle that much easier in means of searching and sorting and indexing your data. Also, it's the easiest way to get to a unique value. If you look at such a person table, you can imagine it's virtually impossible to get any other unique value. Obviously, the combination of first name and last name is not unique. The amount of John Smiths I know is way beyond remotely unique. So it's quite obviously that doesn't work. Even combining in the date of birth won't work. I'm sure you find two people with the name John Smith that have the same birthday. So all these attempts trying to create primary keys from the data you already have in your database are not overly successful, and that's why you typically introduce such an artificial primary key like these IDs, which even in many occasions the database manages automatically for you, so they're just counting up, and that way you're sure you have a unique key. That also points to that these primary keys really don't have any business meaning. They are just a number. There is no business sense to it, and they're not meant to be something with a business sense. So you will normally never show them to the user in an application. They are important, however, for our relationships, and that's where now the other side comes in, the foreign key. Now on the other side, where in your n side of the relationship, where you reference that person, like in this occasion to record a particular contact contact form for that person, you use exactly that ID value. So by having the same value in that PID, which is a reference to the ID on person side, you basically link these two records. So quite simply by saying the ID in the person table and the PID in the contact table is the same, means we are talking about the same person. And you see in these M2N relationships, as again highlighted green here. You also then have the CT ID, which refers to the contact type, to the table up here. So in the end, all you get here is these kind of IDs that ensure that you know which records in the different tables are linked to each other. As said, especially in older database systems, you not necessarily have enforcement for them. In more powerful and more modern database systems, you get a concept called referential integrity, which ensures that you can't do anything in the tables that violates such a relationship. So, for example, in this contact table, you couldn't add a record with a person ID that doesn't exist on this side, on the person table. The other way around, you couldn't delete a person from that person table that still has referenced records on this side, because obviously if you were to do that, you would leave orphaned records in that contact table. I'm going to show you an example how in the end that looks like. What I've done here is we start from the person table again. You see here we have our persons with their primary key, and then I've pulled together a query to combine these three tables, person, contact, contact type. Again, how this whole querying works, of course, we learn in a separate lesson. But now what you see here is these IDs. So you have here, for example, Susan Baker, which has the ID in the person table 6. And you see, if you go over here, there you have the PID, which comes from the contact table 6. And you have the CT ID 1, which comes from the contact type table, which is over here, the 1. And so if you go down each of these lines, you can see these links. Again, of course, you normally won't output these IDs to the user because it's of non-relevance to the user. So you will normally hide these columns. But to demonstrate how the primary and foreign key structure works here, it's quite handy to see these equals. Good, so that's about what we need to know about primary and foreign keys. There's a few other constraints worth mentioning briefly here. On the one hand, there is something called a unique key, which is kind of like a primary key, only with the difference you can always only have one primary key in a table, where you can have multiple unique keys. It means that the values in such a column need to be unique. It's a tricky one, and I tend to use it very scarcely because in many occasions things are not as unique as you think. Obviously, if you were having a database table that holds login details, you would have to have such a unique criteria, like you would say the login name or the login email address needs to be unique, so that a particular login name, a particular login email address clearly links to one account in your system. So there's scenarios where that makes sense, but there's other scenarios where people tend to think, oh yeah, let's use a unique key there, and it effectively delimits things in a unsuitable way. Another constraint mentioning here is the not null we've seen elsewhere already. So these diamonds in this representation here, you see if I go on them, at some point there it shows up if it's diamond, the diamond is hollow. It can be null. If it's not hollow, it can't be null. So that means these fields are mandatory or optional. You get all kind of extended constraints in database tables, like you can constrain a list of valid values on it or a range of valid values. You can have default values defined, so if you don't put any data into that cell, what kind of data does it get, and so on and so on. There's a whole range of options you can do. Good, the last thing we should mention here is on the primary keys. As I've just said, there can always only be one primary key in a table. These primary keys though can be composite primary keys. That's what you see in this table actually. The fact that both the PID and the CTID have that key shows that it's actually a composite primary key. So that means that unlike in the other tables where the value in that one column, ID for example, needs to be unique, here the combination of PID and CTID must be unique. Which means you can per person only have one entry of a particular contact type that you've defined up there. So for example, you can have per person only one telephone number or one mobile number or one email address, one physical address. That may be for certain purposes too rigid, and then you need to open that database design. As you can see here, we can take that further in that project person table and have a triple composite primary key. Because that table describes a person being assigned to a project in a particular role, that seems to make sense. So a person can be assigned to a particular project and a particular role, and that together needs to be unique. You don't want to duplicate such records in a table. If you wouldn't have a composite primary key, you could enter me twice in the project website as a project manager. Well, that would look a bit silly in lists you create later. So the primary key here, the composite primary key, makes sure that you don't end in these situations. So there we have our overview on primary key and foreign keys. And again, once we start writing queries, it's important to understand this concept so you know which data you pair up with each other to create your or to use your relationships to pull your data together in a sensible way. Let's have a look now what database querying is all about. It obviously starts from your relational database, like you can see in this diagram. So this relational database has a set of tables and their relationships. And this particular here is about people involved in projects, with the role they have in each project, with contact details like telephone numbers, email addresses, and so on. Database querying is of course all about now getting to see the data in this database. So we want to pull together data from one table or multiple tables to output them in an application front end or the likes. And the easiest way, and as a developer you do that all the time of course, is using a SQL editor to execute your queries and see the data in your database. I'm going to show you a few examples here. The simplest example would be outputting a whole table, like here's a person table. So we have our 6 people in there with their first name, last name, date of birth, and so on. Obviously we need quite often a more sophisticated view on data, and that's what we see in that second query. I'm not going to go into the details of the query because we learned that in separate lessons. But what you see here is now you get an output of people with their contact details. So we have Sue Barker with an email address and a phone number, Joe Blocks with an email address and a phone number, and so on and so on. So as you can see here, database querying is all about pulling the data together and getting to see the data in our database structure. We should note that database querying is not just about reading the data, but if people talk about database querying, they also mean queries that actually insert data into a database, change data, delete data, and so on. And finally, you also use database queries for all kind of structural and administrational tasks on a database. Let's take a look now at the ANSI SQL standard and the role it plays in SQL querying. With a whole range of database products around, it's not quite surprising that each of them have developed their own subversion of SQL as a query language. So you get PL SQL in Oracle, you get T-SQL in SQL Server, and so on and so on. At the same time, the ANSI SQL standard has been around for a very long time, and all major database systems these days are compliant with the standard, which means they satisfy all the requirements of that standard plus add their additional proprietary bits to it. The most important version of the ANSI SQL standard, no doubt, is the SQL 92 standard, which refers to the year when it was published, 1992. And that standard really covers the whole core, all the things that you normally will need and what we will cover through the various lessons in this course. There's been a couple of updates since and additions, but they are all more exotic and specialist applications. So you really want to concentrate on the SQL 92 standard as the core work you will need all the time. So let's look at a few core features, core principles of SQL as a query language. The most important aspect really to keep in mind all the time is SQL is a set-based language. What does that mean? If you look at this rather simple statement I've put in here, select star from person, it returns a whole table with all its content. In a procedural language like C#, PHP or the likes, Java, you would have to write a loop to output all these data, because you would work with individual records, with individual fields in your records. So as opposed to that, SQL runs on a set of data. That in turn means, as a rule of thumb, that the simpler your query is, the more data you get out. So as you can see with that select star from person, we get the whole table. If we want less of that, we need to make our query more complex. We need to add to it, like what I'm going to do here now. I'm going to add a filter on the manager ID, where manager ID equals 5. As you can see here, we have a couple of records where the manager ID is set to 5, and we have a couple where that is not the case. So if I run that query now, you see we get less records. Now if I want to drill that further and say I actually only want one particular record out, I'm gonna filter on the primary key, and I use the 5 again because that is our manager we've just looked at, and see now we only get one record. So really, as a rule of thumb, you can say the simpler your SQL query is, the more data you get, the more complex it gets, the less data you get. And that is really an important idea to always remember when you do SQL querying. Often enough you see people starting to write some kind of looping features, and that kind of shows that there's been a misunderstanding how SQL work. So to summarize that, again, in SQL you work with sets of data. In this lesson we now want to get us an overview of the main commands in SQL. There's a couple of different domains, but probably the most important ones are DML as in data manipulation language and DDL as in data definition language. So we start with the DML, and I'm just going to make a few remarks here on that screen as a wee reminder of what we're up to. Each of and any of these commands, of course, are explored in much more detail in the various further lessons we're going to look at. The most important DML statement is the select, which allows us to select data from different tables, one table, multiple table, and so on, with all kind of filters, with grouping, with sorting, and so on. By far the most important and most powerful command in SQL. On the other hand, we have three more commands here which are core part of DML, and that's why it's called data manipulation language, and that is the insert, which allows us to insert new data into a table. Then we have update, which, as you would almost guess, allows us to change records in a table. And finally we have delete, which allows us to get rid of records in a table. It's worthwhile mentioning that all of these, as everything in SQL, is set-based, and we're always talking about full records. So you can't delete an individual field in a record. You can only delete a whole record. And again, of course, you can delete a whole set of records. You can delete all records in a table. We're going to go back to that at a later stage. Right, so that is DML. And then we have the data definition language. Now, in the data definition language, we deal with all those bits that do something to the structure of your database. So that is all about tables, views, stored procedures, indexes, and a couple of more things, but that is the most important ones. Maybe one more I should mention is database. So obviously you can create a full database and you can get rid of a full database. So that is the areas DDL covers, and then in each of these areas we have a triple of commands. The first one is a create. So that allows us to, for example, create a table or create a view, create a stored procedure, create a database, create an index. Then we get alter, which allows us to change these things. So if you want to change a table structure and so on. So I would make the remark here already, I avoid the alter functionalities, because once you have an operational database, often enough trying to alter a table that is part of relationships, it causes a lot of trouble. So often enough it's actually easier to say we drop an element, a database object, and recreate it. So drop is the last one out of that series. Obviously you can get rid of any table, view, stored procedure, index, or the whole database by dropping it. So that really is the core overview to your SQL language. There's other bits out there like transaction management, there's specialist commands in each and every database systems for more advanced features like replication and so on and so on. But we are gonna leave that here, and obviously in the various other lessons we're going to concentrate on in particular the DML, but also going to look at DDL at some point. In this lesson we want to look at a few query tools and why you want to use them. I'm going to show you MySQL Workbench and PHP-MyAdmin because I'm using a MySQL database here. But you find similar tools for .NET, the likes of Visual Studio, SQL Server and so on. So why do you want to use a query tool? Obviously, when you do web development with the likes of PHP and .NET, you will eventually execute SQL queries against a database. But until you have these queries pulled together, you need some tool to play around with your data, with your database. And that's where these SQL editors come in. They're extremely handy for ad hoc querying, so I can just go by here and say I do a select star from person and can execute this, and I see my data. Also, I have this information here about my database structure, so I don't need to remember all of that. So for example, if I can't remember that the table is called person, I can go here and say, there's my table person, and I can just double click and you see it adds that. Or I can simply go by and of course take another table and do that. So that way I can do very quick ad hoc querying on the database to find out where my data are, how they look, and so on. More importantly, in these tools I can save and reload queries. So if you build your queries and test them, you don't want to do that from scratch every time again. So instead of writing from scratch, I can load a query that I've done previously, which I'm going to do here now. So you see in that toolbar I have an open one, and there I can use a query, and obviously because I just done something else, it asked me if I want to lose that or not, and here I just say I don't need that anymore. So I open my saved query, and now I can execute that query. So that way I can build a repository of such scripts for all kind of purposes, including creating my database in the first place and so on. That's where I use these scripts all the time, because it makes it so easy to move databases around between different web servers and so on. You just keep a database script that you can execute elsewhere. And equally for all kind of testing purposes, I like to have these kind of scripts where I've pulled something together and I can just run this without having to think a lot about it anymore. The other interesting bit I can do here is I can mark part of that query and say I forget about my where clauses and my ordering for now, and I just want to execute the selection. And you see then I get a different output, not a particular sensible one. Why that is a bit strange, we are going to discuss at a later stage when we talk about joining tables. So you see these tools come in quite handy for a lot of activities, and of course you can save your script again, and in your file menu you will find a save as and all these kind of things. In some database query tools you can even call scripts from another script, so you can build your own library of scripts that call each other and build quite powerful functionalities. So that's our MySQL Workbench. Now I'm going to show you similar things with PHP-MyAdmin. PHP-MyAdmin is probably the most commonly used administration tool and query tool for MySQL databases, because on most commercial web servers you just get that available. It's a free download, you can stick on your machine, and it's very easy and straightforward because it's obviously a web-based application. And you see when I'm on there, I can see my database tables again, I can see structural informations about the database, and I can go on an individual table. So we take our person table again, and I can see the data there, and also I can run a query. So again I have my SQL query window here, and you see by default I already get some query put in there, and now I can say I want to query that by, for example, filtering on the manager ID equal 5, for example, and say go, and you see then I get a reduced set of data. So I can play around with all these things here equally, and I can write queries. PHPMyAdmin is not quite as good in saving individual queries and loading individual queries. You merely have to do that by copy-paste out of this window. But another interesting bit where PHPMyAdmin is quite helpful is for importing and exporting a database. And I'm going to go on the whole database view back, and now if I go onto that export tool, I get a long dialog with all kind of features where I can decide which tables I want to export, whether I just want the structure, whether I want the data, and so on. And I can save that in a file, or I can output that on screen here. And then I get a long script, which I'm not going to bother you with the details right now. But that is exactly the kind of database dump which then in the next instance allows me to save this in a file and reuse this, for example, to import the database somewhere else. So obviously there's an import function in the same way. So you see there we have two such tools that are quite handy for a lot of purposes. When I use PHPMyAdmin a lot, which often happens when I need to work on remote web servers, as said, I will just copy-paste my queries into a Word document, a Notepad document, something like that, just to keep them, because it's just easier with PHPMyAdmin. But in general, PHPMyAdmin is a very useful tool, and it's, as said, the most common one available in the market. So that's given you a little bit of an overview to some query tools. As said, you find any of these in any database system, with any database system, with slight differences, but the idea is always the same. You can see structural elements of the database you're querying on. You can write queries, you can construct queries, you can import and export queries or the whole database. And that way you have your tool set on hand to start working with the database. And of course we're going to use exactly these tools throughout all the various lessons to learn how we query the database. In this lesson we're going to get started on the select statement. And because there's a whole lot to the select statement, we're going to concentrate here on the most basic use of it and look at more advanced versions in various other lessons. First of all, let's have a look at our database schema that you can see here, because that is where, of course, we're going to use the select statement against. So what we have is a couple of tables here, all surrounding personnel involved in projects with contact details on and so on. So let's start with the most basic SQL statement, which is the select star from, and then we pick a table. So let's start with the person table. So if I execute that, you see I'm getting the whole table, everything that sits in that person table. Now move that a bit down so we see both the query and the result. So that gives us, as you can see from the diagram, every single column that is in that table, and it gives us over here, and it gives us all the records. The same we can do with, for example, the project table, which then would be select star from project. And if we execute that, you see we have 3 projects in there. This is a good way of familiarizing yourself with a database, so I'm going to show you the other tables quickly. So we have a role table there. Select star from role, and you see we have 4 roles: project manager, product manager, developer, tester in here. Now what else do we have? We have the contact type, and you see we have the ability to record emails, phone numbers, addresses, and instant messenger there. Right, and finally we look at these intermittent tables, the M2N relationship table. So we have contact and project person. So we have the contact table, and there of course you see the individual telephone numbers, email addresses, and so on, and the foreign keys they relate to. So, and the last one, as I just said, is project person, which shows which persons are matched to which project. And you see that only just lists the various foreign keys from the 3 tables that we've matched together. So not overly useful in its own right. So let's stick to the person for now. So as you see, we see all the content of the person table here. One word of warning at this stage: while this is a good way to familiarize yourself with the database, you really shouldn't use something like this in your web application code. I get this kind of question on quite a regular basis when people ask about performance implications, or find that an application they've written is rather slow. And when I look into the code, it's one of the common things I find. People do a select star from a particular table, and then within the application filter out what they really want. That is kind of defying the whole purpose of SQL, of course, where you really, within your SQL query, within your select, should filter down on those data you really need. And of course that's subject of various further lessons to see how we can do this. So as a rule of thumb, don't use select star from any table in any program code, because you're basically just shuffling a whole pile of data over the network when surely you don't need all of it. This here is a reasonably small table, but if you consider in a big production database you may have thousands, hundred thousands, millions of records sometimes, and if you drag all them over the network, it's quite easy to imagine what kind of network load that produces. And it's pretty sure that you will at no point in an application display all those records. Equally as if you look at this one, it's unlikely, for example, that you display the primary keys in your application, so you may not need them. Or this foreign key on the manager ID. If you want to visualize the manager to a particular person in that table, you surely want to see the manager's name and not his primary key. So this is really the most basic SQL statement, as said, only for diagnostic use really. In this lesson we now want to see how we can start to filter and reduce our record set beyond just using a select star. And what we're interested here is to filter on the columns we have. So we only want to see distinct columns. How do we do that? Simply by replacing the star with a comma-separated list of what we want to see. So, for example, first name, comma, last name. Now if I run this, you see we only get those two columns. And I can further extend that to do another one. An interesting aspect to see here also is that we can rearrange the order. Often you find that in databases columns are not in that order as you probably would like to see them or use them in a report. So we see we can select them in the order we actually like to. And that of course in as many variations as we want, with as many as little columns as we want, and especially while you're playing around with these things, often enough in between you will go back to the select star to see what you all have. The next thing we want to do is we want to filter on the manager ID. And you see now we only get the manager ID. One thing that of course in this situation is a bit funny is that we get all these duplicates in there, and quite often you want to have such a list but without duplicates, and select has a special attribute for that, which is called distinct, which you put in here. So that will filter out every duplicate records lines in our output. It's important that the distinct doesn't work on an individual field but on a per line basis. So duplicate lines that are identical in all columns you display are merged together. So if I run this one, you see now we end with the 5, 4 and the null value in there. If now, for example, I add the first name to it, you see what effect that takes. You see now we get multiple 5s in again, because there is multiple people in our table that belong to the manager 5 but have different first names. At the same time we've already have a distinct, because if I take that distinct out here again and run that, you will see that we see more records. At the moment we have 5 records. If I run that, you see we're up to 6 records, because we have 2 Jennys in our database. Again, going back to the star, shows you what we are looking at. We're having Jenny Palmer and Jenny James. And the way I've just been playing around with here is really the way how you want to build your queries step by step, by looking forth and back and double checking that actually your query results in the right things. You can see even a simple distinct already creates some interesting effects, and you really want to test these things properly and not just believe that you got it right. So always make sure that you compare the output of your query with the original data and manually reconcile that actually it squares up. So there we have a couple of these scenarios with using different columns, and that way delimiting our query output. As you've seen, we still query on all records in the table. We haven't filtered on that. We're going to do that as a separate stage. once you've started filtering on your columns, your output in your query, instead of using the star, it won't be long until you want to do a bit more formatting to that. You may just want to output part of the column content, you may want to do certain calculations on the columns, like on date columns for example, and also you may want to order your output in a certain way, and that's what we're going to look into in this lesson now. So we're going to start with some textual operations. So obviously, if we're starting again from our select first name, last name, we get our list of people in our table, and we may just want to actually only have the initial of the first name. So one way to do this is using the left function and say we only want one character from the left. And you see there we get our initials. I should remark that a lot of these functions unfortunately are not very standardized between different database systems. There's slowly but surely a consensus growing, and you find more and more functions across platforms, but unfortunately the standardization in this area has never been very good, so you may want to look around in your particular target system what works best. An alternative to the left is the substring, and that now needs two parameters, the start position and how many you want. So interesting to remark that this is not zero indexed as many C, Java, .NET like languages, but it actually the first character is the index 1. And you see, there we go, we have the same output on a different way. Now the next thing we want to do is to combine the output from various columns. On this occasion we want to concatenate the first name and the last name into one output field. While some database systems have a plus operator or things like that, MySQL doesn't have that. It has a function called concat, which also exists in a lot of environments. So we're going to concat first name with a space, and the last name. Now if we run that, we see we get our first name and last name nicely combined into one field. There's a lot of occasions where you like to do things like that. Next we want to have a play a bit at some date related functions, and unfortunately there even more so the compliance is a bit limited, but nevertheless it's an interesting area to play with. So we're going to reduce that one here to the basics, and obviously we use the date of birth we have in here. Right, now the first thing we want to do is we say we are only really interested in the year of birth, not the full date of birth. So we can use the year function to reduce that, and you see there we get our years plotted out. An interesting side effect of these functions used on fields is that you can actually create multiple such calculated columns, as they are called, based on the same database column. So for example here now I can say I want also to see the months of the date of birth in a separate column. And of course that leads kind of straight to the idea to say I probably would want to know somebody's age. That's where it starts to get a little bit more complicated. So I'm going to take this one away. And we use the date of birth again. Now there is a function called now available in most database systems, which gives you the date and time of this very moment in time. Now if you use that, you see it creates some rather interesting number, and the way it's negative points to that we've actually just, of course, done that the opposite way around. So nice relearning effect on the side. We'll correct that and turn that around. Still, it is some wild number, and depending of database system, it's something like the difference between the two date values in days or the likes, depending on how the data types are coded in that database system. Now you could be tempted to say, maybe if we want to see the age, we just put a year around this thing, and that would convert us this number in there in years. Unfortunately, as you see, that doesn't work. One first way to do this here is to actually extract the year of both individually and run that. So we take the year of now, so this year, minus the year of the date of birth. And we run that again. So there we start to see something in that direction, what we're after. Of course, when you start thinking about this, you quickly find out it doesn't really work, because obviously it doesn't take into consideration if the person already had their birthday or not. Well, there is some help in the system, of course, and that is using the dateDiff function. So we use dateDiff, and that wants to have two dates. And again, it's not uncommon. I'm always good at not remembering which way around it is. Never mind, just try it out and you see in a second. And you see, well, that's a positive number, so obviously we've done the dateDiff the right way around on this occasion. So, and that will give you again something in some unit depending on the database system. On MySQL it happens to be days. So obviously now we can divide this by 365 as an approximation, taking into account that it's not ideal, because obviously we have leap years and there's plenty of ways how you can play around with that to optimize that if that becomes crucial. But you see, now we get actually a date that looks more towards the right direction. And if we apply another function now, then we can actually get that into a straight year to be able to see a rounded year. And that function, guess what, is called round. So there you have your rounded dates now, and these one of course are now proper dates that are a bit more sophisticated than the first way. What you've seen nicely here is the way how to attack this. Never try to build things all in once as one big approach. Always do these things in small steps. Add one function, see that it does, and then wrap another one around and wrap another one around it. And that just is an approach that is most successful. And whether you call that agile or whatever, doesn't really matter. I've been using that kind of approach for many years. Don't do big programming codes in one block, but do it step by step and test and see what the outcome of it is. So here we've seen our date activities. Okay, and the last thing we want to do in this lesson is we want to look at how we can order our output. So I'm gonna reduce this one back to a simple date of birth. And there we go, we see our base output as we already know that. Now, how do we sort or order our output? There is an order by clause in SQL. And then we say by what field we want to order the output. And it's good practice to be specific about whether you want to have it ascending or descending. The descending would be DESC. For the simple reason that sorting orders are set by the database administrator. There's typically some default in each database systems, but the data administrator can change this if they see fit. So if you want to be sure that your query always outputs the data in the right order, make sure that you always specifically mention ascending or descending. So if I run that, you see now we have our output ordered that way. Good, in the same way I could use now the date of birth and for example use the descending there as a way to say we want to have the list ordered by date of birth, and we have the youngest at the top and the oldest at the bottom. And you see there's one person that doesn't have a date of birth set in the system. Now the next thing we can do is we can actually order by additional criteria. We can order on multiple criteria. For example, I could say I want to order on the first name in ascending way first and then on the date of birth, which means I first order on the date of birth, first order on the name, and then I order within same name on the date of birth. And because we only have one first name double, which is Jenny, of course the date of birth order only grabs on that level. Now another thing I can do here is I can order by a criteria that is not even in the output. So my order by criteria just only depends on the database table itself and not on what I have in my select clause. So, but to see what we're doing, I'm gonna quickly add the manager ID to it because we want to use that as a criterion as well. So, and now what I'm gonna do is I'm gonna say I want to block my date of birth by manager ID. Output, oops, there's a space missing. So now we order by manager ID first, and within the manager ID we order by date of birth. So we see now we have on the manager ID 4 we only have 1, on the null we only have 1, and then we have multiple on the 5, and it orders that way. So, and to show that effect is I can take the manager ID out of this here now, and it still runs and it still creates the same output. So that can be quite a helpful way of doing things. Though of course it can have a tendency, if you do something like that, that your output looks strange because you can't really see the motivation for the sort order. But nevertheless there's a lot of situations where you're going to do things like that. So that is really all we need on the sorting orders, and that way you can sort your output in your select statement as needed. Which leads us to the end of this lesson, where we've looked at the various ways of formatting your output in means of formatting individual column output, creating calculated columns, consolidating multiple columns in one, and of course sorting our output. In this lesson now we want to introduce column aliases and see a couple of examples where they come in handy. So we start again from this kind of query that we've used a number of times, getting first name, last name and date of birth out of the person table, and you can see the output down here. Now the first way of using an alias is if you actually would like to change these column headings, because that is what the aliases are controlling. If there is no alias, as in this occasion, it's simply the column name. Now how do you do this? You add the alias to each of the database columns just behind it. The original official notation is using the word as, though it is actually optional, but I show it on this one, and then you basically put in there the name you want to use. And for example on this occasion I'm gonna use the word Christian name. Now I'm gonna run that to see the effect, and you see now it says Christian name here instead of first name. Now obviously the thing with the underscore in there is maybe not the most beautiful one, so I'm going to show you another one, especially if you want to have the ability to put something there with spaces, because obviously, as you can see here, the space has its meaning in separating the column name from the alias. If you don't put the s in there, you're going to put that alias in single quotes if you want a space in there, like for example if you want to say last name. Again, execute this and you see now the last name pops up there. Or if it's just a plain word, then you can just put it behind it as this, like calling the DOB date of birth, simply birthday. So there you see the kind of three main versions of creating an alias, and of course for simplicity most of the time you're going to use the last one, and only if you have spaces in your alias you would use the quoted one. I generally would discourage spaces in these names because they cause all kind of troubles once you start using that in a web application from PHP and the like. So and especially the idea of having a nice looking readable label then of course becomes obsolete, because your web application is going to take care of that. Right, let's clean this out a bit again so we get a bit space, and then we're gonna do a second version of aliases, and that is now for all these kind of calculated or computed columns that we've seen elsewhere before. So if again I say I just want to see the initial of the first name, and I use my left function for that and execute that, of course you see that kind of formula I use turns up as a column. Now that in particular is gonna cause havoc if you use that from PHP or .NET or the likes to actually read the data, because you're getting as a column name something rather complex and potentially conflicting with your programming language you use. So you really want to use an alias on there, which then is what you use in your web application programming language. So of course here I would just call that initial and run that again, and you see there we see our initial. Now this initial also comes in handy for our sorting. Remember, we need the order by clause to sort our output, and usually we would have to copy that bit down here and stick that in there, which is, especially if these calculations become a bit more complex, is a real nuisance, because you may change the query and forget to do this. With the alias in place, we can just simply use the alias here and put that in there, and then run that query again, and you see now our list is sorted by the initial. So there's a couple of usages for column aliases, and of course you can have multiple and as many column aliases as you want in a query, and you can use them for all kind of interesting additional aspects and means of output, and more importantly in many web development areas, to make sure that all your columns have a easy, simple column name that can be used within your web programming language. In this lesson we want to look at the where clause and learn what the where clause is all about in a SQL statement. So what we're up to here. Obviously we've seen before a couple of times, if we use our select star from person, we get the whole table, which on this occasion only has a handful of records, but may just as well in a real production database have lots and lots and lots of records, and typically we don't want to see all of the records. Instead we want to pick dedicated records, dedicated lines out of that, and that's where the where clause comes in. Now there's tons and tons of different ways of using the where clause, and we're going to cover that in a few further lessons from here. So at this point we just want to look at the real basic version of doing that. The easiest way to get your hands on exactly one record is by using the primary key. Now if I have a quick look back into our diagram, here we have our person table, and you see the ID field is our primary key. So if I filter using that one, I'm going to get exactly one record. So I put in my where, and then I put a where condition, where ID equals, for example, 3. Now if I run this query, you see I get exactly this one record returned here. And that I can continue in various other ways. Now it's probably a good point here to actually highlight one major feature of SQL as a language, that is that it's a very modular language. So while we are looking at the where clause here, we can still use all the other features we've learned elsewhere or may still learn elsewhere. For example, of course, we can, instead of using the star, reduce our columns to what we want to see. So we can do our first name, last name, and date of birth, for example, and still filter on just the record with the ID 3. And you see then we get just those 3 columns for that particular record. Also what you see nicely here again is a general feature always to remind in SQL, whatever you use in the filter doesn't need to be in your output that you've selected up here in your select statement. So this is these are independent aspects of your query, and you can build from these building blocks whatever complexity you fancy. I could, for example, instead of filtering on the ID on the primary key, which will always give one record because that's the idea of the primary key, filter on something else, like for example on our manager ID. So if I run this, you see I get an empty result because there is no manager ID 3. You may recall from other exercises that we have a manager ID 5 quite dominant featuring there. So there I get these records. And equally I can now add other bits to it, and we learn much more about this along the way. For example, I could add a second condition here, saying I only want to see those with a first name equaling Jenny. And you see now we've reduced this to 2 records. And again, at any point in time I can just as well say, no, I want to see all because I'm trying to find out something, and I use the star again. So you see, that way I can play around with the different aspects of the where clause, and either way the purpose of the where clause is to reduce the number of records I get in my result set. In this lesson we now want to look at the various kinds of filter conditions you can create. We are still not going to cover all and every possibility here, but we are going to cover a much more detail than previously. So if seen before, we can simply filter our query result on the primary key, like here ID equals 2, and that returns us exactly 1 record. Now we also get an unequal. So we may want to use that to find everything except the 2. And you see now we have all our records in here except the 2. I should point out, and it's often a matter of trying, there is another version of unequal, which is the exclamation mark equal. And you see that works here as well. These two alternatives of the exclamation mark equal and the smaller larger are in generally both supported by the standard, but individual database systems are varying what they support. Most of them support both now, but you may find that the odd one doesn't. So that is the equal and the unequal. Then we're going to have something like a larger, so everything where the ID is larger 2. Quite straightforward. You see the 2 is missing now. Larger equal, of course, including the 2. Then we get a smaller, and I get my shift keys mixed up again here. So the smaller equal, the smaller, of course, excluding the 2 again. And that, of course, you can do on all numerical values, but you can also do things like that now on the names, on the text values, and we're going to do that next. So obviously you can do a filter on the last name, so we could say on blocks and run that, and we see we still get that 1 record here. Equally we can use smaller and larger now, and we're going to do that and see what happens. And you see then we get everything that in a literal order, in an alphabetic order, is larger than blocks. And again we can use the smaller large and the larger equal, the smaller equal, and all these variations. The important bit is to remember this is doing an alphabetical, a lexical ordering. Now you can also do this by, for example, saying I'm going to put, say, the M is somewhere in the middle, and you see you get all the records that are M plus whatever. So it's not, as you might expect, sorting on single character fields. The length of the string doesn't matter, it does an alphabetical filtering here. Good, and the next option we want to look at here is doing a similar thing with dates. So we have the date of birth in here, so we can do the same there. Now the important thing is, and that's where date values become a bit interesting when you use them on database, if you use them in a SQL query, you're going to have to use exactly that string representation that you see here. If you're lucky that your database sits in different parts of the world with maybe different localization settings, then that format may well vary. So it can be a bit a pain to do that properly, just as a warning. It's gone a lot better in recent years. It used to be that bad that years ago I just plainly didn't use data values on databases. I just coded my dates in Unix timestamps, so this date here would have been 1918, 08, 20, end of story, no hyphens, nothing in between, just as a number. It's getting much better, and you find more database systems using dates properly and coding them. So again, you see now I can sort on that one, and equally I can do now the larger or the smaller. See, we only have one larger ones, we have a couple of smaller ones, and that way you can filter on different date areas. Good, and then we have one more option which is mostly applicable for numbers, but in principle available in other areas as well, and that is the between operator. So if we go back to our ID, between, say, 2 and 5. So that returns us all records where the ID is in that range 2 to 5, and you see, if in doubt, easy to find out by testing it, it's inclusive. So some people will say here between may think of an exclusive. The between here is an inclusive between. So the 2 and the 5 is in the range. If in doubt, it's always good to test this. I don't tend to trust documentation on this left alone. It can be tricky to find it in the documentation. So if in doubt with any of these features, I just quickly run a quick query to find out what it does, and then I know, yep, I've seen it, that's how it does. Good, and that is really our main filter conditions on numbers, on strings, and on dates with the equal, unequal, smaller, larger, and the between. Let's have a look now how we can combine multiple filter conditions. So we start out again, of course, from our select star from person, which gives us a whole table, and then we add a where clause. For example, we want to filter on the date of birth being larger, say everything after 1970, so 1970 1231. oops, 0 dot, and so there we see we get 3 records. Now if we want to filter that further, we can use the AND to create an additional condition. For example, we could say manager ID equals 5, and you see then we've cut out one more. And we could go on and add another one, for example, say ID larger 1, and then of course we're going to cut out the first record. So that way we can combine multiple conditions, and that we can do with an AND, or we can do this with an OR. So again, if we do this one with the AND, first of all, you see we had reduced that thing to our manager ID 5. Now if we use an OR, then we're going to see we're going to get a different answer, because what happens now, we get everything where the manager ID is 5, irrespectively of the date of birth, and we get everything where the date of birth is past the end of 1970, irrespectively of the manager ID. And that is an important thing to realize, and often a bit tricky for beginners in programming, that the logical AND and OR are kind of the opposite way around as we would talk as humans. If you would go in a shop and say, I want apple and pears, you basically mean you want apples and you also want pears. Where if in a where clause you would do this, you would never get a result, because you would basically assume that a certain field at the same time is apples and pears, which could never be. So in a logical sense, what you would actually mean is a where clause with apples or pears. Which of course, if you say that in a natural language, you actually mean the AND condition. So that's kind of important to remember, that that goes kind of the opposite way around. Now the other thing we can do, of course, though I would always call for caution with that, we can mix AND and ORs. So we could say again this one, and then we could use our ID larger 2. Now one thing I would say about this one is that that's not very good practice, because in the end the question now will arise, how is that interpreted? Is that date and birth and manage ID, or ID, or is it date and manager ID or ID? So by not kind of expressing it, you rely on how the database will favor the AND and the OR. And quite frankly, you don't know. So you see, it creates a result, but in the end, if I do something like this, I would always say I want to be straight. So I normally would put brackets around that, for example here. So that way I would say, well, I want every person with a date of birth past 1970 assigned to the manager 5, and in addition also, that's why I have the OR, I want everyone with a ID larger than 2. And you see, then I get that. So I have all my 5ers here past 70, and I have that one as well, even though it's not past the end of 70, but it's an ID larger 2, because it's the 4. And I have another one here, which is the 5, which equally goes for that. And I get the null value in there, because again it satisfies the condition of the larger 2. So you see it's getting a bit complex to deal with these things, so you want to be careful. And in reality, I've not often find situation where you really want to mix the AND and the OR. But if you do, be sure that you use these bracketing. So now in a similar way, I could go by and say, and I probably would actually stick that in a different line then. Of course, takes a bracket down as well. Yeah, and would say, so now I want everyone born after the end of 1970, and I also want everyone who belongs to manager 5 or has a ID larger 2, and so we're gonna get a bit of an effect here. I'm gonna actually change that to larger 5 and see what happens. Right, and you see now we get a complete different scenario, because now we have the AND in there. So we only get persons after 70 and filtered down by additional criteria. So if I go back to the 2 here, you see it still doesn't change, because there is just these 2 people with our date of birth in there. So what you see nicely here on these various examples is, yes, you can mix the AND and OR, but you really want to test this very thoroughly and go back on your base query and say, does that actually square up? So by basically just using your select star, mark that, and then you can just run the marking. You can go back on your full list and qualify if actually that returns what you want. Never blindly trust in these AND and OR conditions. It's so easy to get wrong. Always make sure you test that very well. So, and that's really all that needs to be said about our combined filter conditions. Let's look at a few more filter operations in this lesson. So we start again from our select star from person, which you see again all our data in that table here. Now the first one I want to show you is the check on null values. You see down here we have all these gaps where it just says null, which means these fields are empty in the sense of a database empty, so they've not been touched at all. There's not an empty string in, there's just nothing in there. And now you can check on these values by using the null operation. So we're going to do that, and I'm going to start with the manager ID case, where manager ID, and now the difference is that it's not an equal, but it's called is null. And now if I execute that, you see I get that record where the null is. Equally, I can do a is not null, which then gives me all the other records except the null record. Ignore the bottom line, that is just a thing in that workbench tool here where you can actually add a new record. So equally, of course, I can do that on every other field. So that is our null and not null, which comes in very handy for finding these kind of gaps in your data, which often enough you want to know. While on the one hand in the database design somebody has decided that a certain field is optional and as such can be null, often enough you will want to find out where these gaps are and see if you can fill them in. You see, for example, here is a database, date of birth missing, and you may just say, well, it would be nice to complete that and fill that in. Right, so that is the null operation. The next thing we want to look, and again I'm going to start from the base query. The next thing we want to look at is further text operations. Aside from the usual equal on a fixed string, we have something called a like, and that comes in a number of flavors. I'm going to use the notes column here actually on this occasion, and I want to search on certain elements in there. The like has the idea of a wildcard style search in it, and very much is used in kind of the likes of search engine style queries. So where nodes like, and then I put in a quoted string my pattern matching basically. Now a common one would be this one. I have a fragment of a word, or a word, on this occasion CEO, and I surround it with 2 % signs, which basically means I'm looking for everything where there's something, then the CEO and something else. Including the something before and after is effectively optional, so there doesn't need to be anything before or after, but there can be something before and after. Now if we look at our records, the one obviously that matches this one is that record number 5, and as you can tell from my comment just, this pattern matching isn't case sensitive. And you see, there we go, there we have our record. Now in the same way, if I can just do the main thing, I could for example say I want to look for somewhere the name Rick is mentioned in, and do it this way, and I get these 2. Or if I want to make sure that Rick is at the beginning of the string, I take away the % here and run that one, and I get these 2. Where if I put my CEO in here again, which we've done before, and run that, you see it doesn't return anything because CEO doesn't sit at the beginning of my string. Right, see the whole table again to find out the next one. Now the next one I could do is using a different criteria. For example, I want to see all last names that have an A at the second character. So I use a where last name like, and now if I, instead of having so many characters which the % expresses, I want to be specific on 1 character or 2 characters, I can use an underscore for each character I mean, and then for example can say A, because I want to have all the ones where the last name has an A on the second character. And then I don't care what else is behind that, so I do the % again. That is important because if I don't, then I would look for values where whatever the first character is followed by an A and nothing else, which obviously here wouldn't return us anything. So, and you see here now we have those with the A in the second character of the last name. Platform specific, there are a few other versions around where you can work with exclude characters and so on, but they are not very standardized, and for example MySQL is reasonably poor on that. Also you find that you can use in a lot of database systems these days a construct called regular expressions, which originally stems from the likes of Perl and these kind of languages, which is a very complex, very abstract formalized pattern matching, but is really a training matter in its own right. So I'm not gonna touch on that here. But if you need very complex text pattern matching, then that is a extremely interesting feature. Good, so that is our like and that is our null. And the next thing I want to show you is the ability to widen our equal in a different direction. And that is the in operator, which instead of equaling the last name to one value, we can equal it to a list of values. So we basically say we want all records back where the last name is either of those values in the list we're gonna put in here. So we could say Palmer and James. Don't forget the quotes at the beginning, that's important. And now if we run that, you see we get those two records where the last name is either Palmer or James, and that list of course can be as long as want. This can be quite an interesting feature, though if you hard code it like this, it normally smells like your database design is not very ideal, because you're obviously looking at fixed values. We're going to see at a different stage that these in queries can be quite interesting, these in filters can be quite interesting in the context of subqueries and more complex queries, where you would create this in list dynamically at the time you're querying. Good, and the last version I want to show you here is that of course in filters you can use calculated values. You may recall that elsewhere we used the date of birth to create a age out of that, and we do something similar here, and we can do that as a where clause. So what we do is we use that dateDiff function, which takes the now, so timestamp right now, and it takes the date of birth, calculates the date difference, and now we want to divide that by 365 again, and that way get our rough date. And one thing again I would suggest here now is to just make things a bit more readable. You want to say larger 40. Yeah, so by putting brackets around that thing you basically can visualize a bit better what's going on, especially if you do this as part of a multi-criteria where clause. That's quite helpful. So that will give us all the people that are older than 40 on here. Now if we run that, you see we have two people on here who are older than 40. And again, be sure to cross-verify that by running the base query. And you see everybody else here, the other three guys, are younger than 40. So there you have a whole range of additional elements you can stick in your where clause and can combine into rather complex where clauses and filters for your query. In this lesson we want to learn about how to count records in a database table by using a SQL query for that. There's a lot of situations, especially in application development, where you, in the first instance at least, you're only interested in the number of records in a particular table or as a result of a particular query. And only in a second instance you're interested in the actual data in there. So how are we going to do that? On this occasion I'm going to leave our select star from person in here so we can see the actual table again and compare what we've been doing. So you see here we have our select star from person with 6 records, and now I'm going to do a select count star from person. Now if I execute that, then you see I get the count 6, which is the records we've just done. So that is the most basic version of your count. Go back to the full table here, and now we want to look at another option. And another option in the count is to actually specify a particular column, for example the notes column. Now you may wonder what the difference is. The difference is that now the count is based on the state of that particular column. We'll say it will only count those records where there is actually data in that column. So the other way around, wherever we have a null in that particular column, that will not count towards the total count. So on this occasion, you see we have a lot of nulls in the notes column, and we only have 2 records that are actually filled with data. So if we execute this query, we see we get a 2. And the same we could do with, for example, the date of birth column. If I run that, we get 5. If we take our other query, our full query again, then we can verify that. So date of birth 1, 2, 3, 4, 5, and 1 null in it. So that way we can count records in our table either in full or based on complete records, and that way can find different counts depending on the situation we want. Obviously that situation with a count on a particular criteria, on a particular column, we could also achieve by using a where clause. For example, saying where not is is not null, and of course the column. So where date of birth is not null. Now if I mark this one again so I can execute it. So you see now we get those part of our table where the date of birth is not null, and of course now we could put our count star around here, and we'll find that that again returns us the 5. So this again is another nice reminder of the modularity of SQL, which means you can combine the different bits and bobs, the different aspects we've learned in different lessons here together to suit your needs. Which on this occasion means we are using the count in our select, and we're using a where clause to specify that. And of course you could drive that on now into using a count on a particular column and having a whatever where clause. So you can use this count in whatever context you fancy. So here we've seen a couple of examples how to use your count attribute in the SQL select query. Let's have a look at some aggregate functions now. We're going to concentrate on those that are commonly available throughout all database systems as specific extensions in various database products, but we're going to stick to the 4 core ones, which is sum, average, min and max. So with these you can consolidate a set of records into these kind of aggregated values. We're going to use the project table here, and which you can see below here. So that has 3 records. It has a primary key ID column, it has a label, and it has a budget. And obviously some of these consolidations really only make sense on numerical values. So we're going to start with the sum, which goes like this. Sum budget from project. So if I run this, then I should get the total of these budgets, which is, if you quickly count with me, is just below 3,250. And there we go. There we got it. Now the next thing I can do is to calculate an average. Which is a bit more tricky to do by heart, but you're going to get there as well. And you see, because we haven't done anything else, and because this column is a double column, of course it will give us a lot of digits. Nothing really to worry about. Either you can use a round function in here to round it to as many digits as you want, or quite often that's something you really do in your front-end application to worry about the presentation of the data in that respect. Good, then we can do a min on the budget. And that gives us the lowest value in our table. It tells us 250. Let's cross-check quickly. And there we see, out of these 250 is of course the smallest. Now if we do the same with the max, then it should give us 2000. And there we go. So you see here, these aggregate functions consolidate all the data we are using in one particular value. And that is really what these aggregate functions are all about. Now, obviously, I've just said certain of these only make sense on numerical values, but the min and the max in particular you can use on textual values as well. So we're going to use that on the label. And again, what the min and the max does, it finds the lowest and the highest value, obviously on a textual value, using lexical ordering features. So if I run this one, then we should for the max get the website. And there we go. And if we do the min, we need to mark this one. We are gonna get the Facebook up. Looking back, we see, yep, that's right, that is the other one. Now, if in doubt, you can always try something like the average, because on some database systems that may actually be supported. And you see here, it's not really, it produces something rather peculiar. Equally, the sum will do. But at least you see it doesn't crash. So it goes back to what I've said elsewhere. If in doubt, give it a try and see what happens. So that is our different aggregate functions, and really those 4 ones are the important one. You find in some database systems more sophisticated statistical functions, for example. You can use in SQL Server in particular, you find the ability to build your own aggregate functions by implementing them in .NET, but that are all proprietary features, of course. Right, the last thing, of course, to mention here again as a reminder is, of course, I can combine that with other activities. So, of course, I can add a say a where clause to this. So we go back to our budget, for example, and now I'm going to add a where clause. Remember, I'm going to show you that quickly again. If we just do the min, we get the 250 as a minimum budget. Now if we, for example, would say where ID smaller 3, we're obviously cutting out that record, and it will obviously consolidate on the remaining records. So in this occasion the 999 should become the minimum, and so it does. A good hint with these kind of activities is always to develop these things step by step. So I would start from my select statement saying, yeah, there's my data. Then I'm going to add my where clause and saying, yeah, that's the subset of data I'm interested in, and then I'm going to do my consolidation. That way I've kind of reassured myself that I'm actually doing the right thing. If you stick too much things in one go in a query, it's too easy to fall over somewhere, miss something, so don't try to be too clever. I've hit the wall more than once in my career with that, and I've learned from it to be careful and do things step by step, and I've been doing that for 20 odd years, and I still wouldn't attempt a lot of things in one go, because you're getting disrupted by something else, you're not having the best of days for whatever reason, you didn't sleep well, and so on. So you really rather want to be safe than sorry. So that's our aggregate functions. In this lesson I want to talk about some do's and don'ts of consolidating data. We'll say what you can and what you cannot do when you use aggregate functions, as there is a couple of constraints what's possible and not. The bottom line really is that once you start using any of these aggregate functions, you need to use them throughout. We're going to see at a later stage when we talk about grouping of data that rule extends a bit, but as long as here we consolidate all data in a record, in a table, into one record, we need to either consolidate all data or none. So we're using our select star from project again, and if I do a select, say, max budget from project, we've of course seen that will give us our 2000. Now if I also want to do a max label, then we're going to see some interesting effect. Let's first of all run the full table again. So we have our max budget is 2000, and now the thing to recognize here is that actually the max label will not create the same column as such. So on this occasion we're actually lucky it will, but it's not because these two values are related. That is two independent queries. So if I run that, you see we get these two values. Now I'm going to modify that, and for example if I say min label and run that, you see we get two non-related outputs. In the same way, of course, I could use a min budget here and run that. Then you see we get two different values consolidated out of that whole table we've been using here. So it's important to recognize when you do such multiple consolidations that the data and the different columns you are showing there are not interlinked with each other. They don't represent the same base record. If you think about it, that kind of makes sense, because with things like an average or so, you wouldn't be able to associate it. If you take the average of your budget, it's obviously some value sitting between any of these records, so you couldn't associate other things with that. So as such, it's important to remember that when you do these consolidations, that they are independent of each other. So you want to be careful to use queries like this, because for the unsuspecting user, it may give the wrong impression. Especially if you do this min and max, it's quite straightforward that people say, yeah, obviously that's two different values. But if you use an aggregation on the budget and an aggregation on the label and output that this way, there is a likelihood that people will think, ah, okay, that is the project with that particular consolidated budget, and misunderstand that. Good, and the other thing that this whole thing implies is that you can't mix here. So I'm going to show you in a moment an example where MySQL is actually behaving outside the standard. So if you were going to do something like that, with obviously the idea, yeah, I want to see the label that relates to my max budget, then that is from a user point of view a valuable query, but by default, the way the SQL standard is set up, that is not possible. So in many database systems, this query will crash and will say, sorry, I can't do that, because it mixes consolidated and non-consolidated data. Interestingly, in MySQL, if I do this, it actually creates the expected result. Now, on the other hand, if I use the average function, as per the discussion we just had, the average sits between two of the three records, so there isn't a sensible label actually to it. So if I run that, you see it still comes up with that label here, yeah, that website label that we've seen before. To take it once further, if I use the minimum, where minimum now of course is Google+, and run that query, you see the label still shows 250. So obviously MySQL does a kind of default consolidation there, which is not really sensible. So as said, in many other database systems, a query like this will just simply crash on you. And here you see it doesn't crash, but it doesn't create a sensible output. And that's where it gets a bit tricky when you have features implemented like this in a database system, that in certain situations it looks like it does the right thing, and actually when you look deeper it doesn't. That's why I generally disapprove of these kind of openings of the standard, because it always fires back on you. So let's stick to the rule to say aggregation only, no mix of aggregation and no aggregation. This one creates a sensible output, as said, with the risk of being misunderstood, but at least a correct output in that it creates the smallest budget out of the whole list and the lexical highest label out of the whole list, which here happens to be the same record by chance, as you can see here again. So that is really the important do and don'ts in aggregation to remember. Always aggregate all or nothing, never mix aggregate and non-aggregate, and actually you want to be careful to mix aggregates at all. By the way, I haven't mentioned that specific, but of course I can do a count star in here as well. And if I do that, you see then I get more information that are not really related to each other. There may be application situations where you want to have that range of data, but be careful and be sure that you know what you're actually getting there and don't misunderstand these data. So that's what there is to say at this stage about do's and don'ts of aggregation. In this lesson I'm going to show you some multi-set consolidation features. We'll say the ability to merge multiple result sets from multiple queries into one big result set. There's a couple of features around like that, but the one I'm going to use here is the union, because the union is the one SQL statement that is in the standard and is available throughout pretty much every database system. There's other features around that allow you similar things in different ways, like an except or so on, that are not necessarily available on all database systems. So what is the union doing? The union is merging two or more query results into one big result set. It comes with certain constraints. The main constraint is that each of the queries needs to return the same amount of columns in your select. So if you happen to have the same structure throughout, you can use a select star, else you need to be specific on the columns. And not only the number needs to be the same, the data types in each column need to be the same. So I'm going to show you that first of all by using two queries on the same table, creating different subsets and then merging them. And afterwards I'm going to show you an example using two different tables to merge data. So we build our base queries again first of all. So we do a select first name, last name, manager ID from person, where, and what we're going to do is we're going to do one subquery that gives us only those with a first name starting on J. So we're going to do a left first name comma 1 equals J, and again we're going to build that modular, so I'm going to test this query first to see that it gives us the right amount. So we see we get these three people. Joe, Jenny and Jenny. And then we're going to build another query which gets the same core structure here. So we're sure we have the same column structure, and we're going to give that a other filter, and here we're going to filter on the date of birth being passed or from 1980 on. So we're going to 1980 01 01. And you're going to see in a moment why I'm choosing that. So we run that one, and you see that gives us Paul and Jenny again. So there we have our two start queries, and now all we need to do after we got these individual queries doing what we want them to do is to stick the word union in between here, and then we can run that whole thing again. So, and you see now we get the 3 J's and we get Paul. So one interesting aspect which I haven't mentioned yet here is that actually the union has an implicit distinct in itself. So it will kick out duplicate records in that union, because in the vast majority of union applications that's exactly what you want. You don't want duplicates in there. Now the good news is, if you want to, then you can put an all behind the union, and then you're going to see the duplicates. So if I run that again, you see now we get a record more, because now we have Jenny twice. And now you also see kind of how the whole thing has built. So you see the first 3 records are the output of the first select, and the second 2 records are the output of the second select. Good, I'm going to take that back on the normal union, because that is what you would normally do. And so there we get our 4 records as we've just seen. Now one thing you would want to do here probably is sorting the output. And that's an interesting one. In a union you can't have an order by for the individual select queries. You can only have an order by at the end, and that is something we can do here now. And we can, for example, say we want to order them by last name ascending. And run that, and you see now we get our records ordered in a bit more interesting way. So that is our union here. So that shows us the ways we can do in such a union. So you see that gives you the chance to basically build subsets of records and then merge them into something bigger. That can be particularly helpful if else it gets a bit complex to write where clauses. Sometimes the union can be an interesting way to do this. Another area where you use unions a lot is in data migration, and that's where the second example I'm going to show you here comes in. So I'm going to clean out all that, because now we're going to do something completely different. We're going to merge data coming from 2 different tables that for our particular reason makes sense to merge. The actual example we use here may not be the most compelling one, because our database doesn't have that. In a legacy database, where you quite often would find that when you migrate data out of a legacy database, you would probably find different tables that have very similar tables in there. You may have address data scattered over multiple tables or so, and you want to consolidate them. What I'm going to do is here I'm going to use the role table and the contact table, because they both have the same structure, and in a way they have a similar idea also. They keep labels along with a primary key to describe something. The one describes roles of people, the other describes contact types for contact details of people. So at least if you stretch it a bit, you could argue you would like to see a consolidation of these ones. And that's what we're going to do here. So I'm going to do a select star from role first of all. And you see there we get our different roles we have in here. And then I'm going to do a select star from contact type and run that. And you see there we get our second list, again ID and label. And now I can union them and run the whole thing. And you see then we get such a consolidated list, which basically would give us a list of labels. And a application for that could be a situation where you say, well, we need to get all these things translated, and we want to give the translator a list of labels that we need, and then the translator can add the same labels in a different language next to it. So there you see one of the very interesting features of a union, that you can actually consolidate data out of completely non-related tables, just because you say, well, it's a kind of set of data that interests me to combine. And the database won't hinder you doing that. So here we have our overview to the unions. As said, there is other versions, like there's an except, which would create, unlike the union, just those records that are only in the one or the other. There is similar things for getting the overlap between two record sets and the likes. As said, these things are not particularly standardized, so if you need anything like that, you will need to look out in your database system if it exists there. The structure is the same. You create your individual select statements, and then you put the consolidating keyword in the middle. In this lesson we want to talk about the group by clause. What's the purpose of the group by clause? The group by clause allows you to consolidate data, but instead of consolidating the whole table, it allows you to group the data by one or more criteria. So how are we going to go about that? We start from our person table again, as usual, and then we can start with the most basic grouping, and we just want to group on the manager ID here. If you look at the table, that sounds like something that might be interesting in a lot of occasions, to say, well, we are really interested on all kind of reporting information per manager. So what I'm going to do is I'm going to do a very simplistic grouping, which is not much use, but we extend that in a moment. And here you see our group by clause comes in. So that selects just the manager ID from that table. Why we reduce it to that, we'll come back in a second. And we group by the manager ID. So that is our grouping criteria. Now if I mark that part and just execute that bit, you see we get that list of manager IDs. And of course that's something you would normally do with a distinct, so that's not something for the group by. What you really want to achieve with the group by is, of course, now per each of these manager IDs you want to see certain information, and that's where the consolidation comes in, because obviously once you group you can only output the other bits as consolidated information. let's remember one consolidation we've talked about and use that here. That would be our count. So if I execute that, remember that gives us the total number of all our records, which is 6 here. Now what we want to do next, I need to open that a bit, is to get a count of people per manager ID. So what we're going to do is we're going to stick the count star in here. So what that means now is we group our records by manager ID, and then within each group we do a count star. So obviously for the 5 we expect 4 records, an account of 4. For the manager ID 4 we expect a count of 1, and also we have 1 with a null. Right, so if I execute this, there you see we have our counts. So that really is the idea of your count. Now we can twist that further, and again I'm just going to pull the original data back up here again. So we see it's always easiest if you see the data in front of you to think about what you want to do. Now for example I could say I want to consolidate by another criteria, like the initial on our first name. We've used that initializing ID earlier, so I'm going to use that again here. So we're going to do a left first name 1, and we're going to call that initial. And then of course we're going to group by initial. One thing you see here quite nicely as well is typically of course you will output your grouping criteria. There is no syntactical need for that, but typically if you don't do that then it looks rather silly, because you get a stream of consolidated data and you can't actually tell where they come from and what they belong to. So typically of course you want to see that idea where they belong to. So you see now we have different counts for our different initials. One thing to show here quickly as well, which doesn't work, is you can't do this part in here. So you can't actually calculate a grouping criteria, or you can calculate a grouping criteria, but you can't use an alias and refer back to that. So if I try to execute that one, you see it fails. And you see by it's getting stuck here. So I'm going to undo that, and you see then our query runs again. So typically in your group by criteria you will use simple criteria, columns, or an alias to something that you've created elsewhere in your query, but you're not really creating complex calculation as group by criteria, because most of the time it doesn't work like that. Right, so now we can of course shift that a bit further and say we want to have a multi-layer grouping, which of course is what you do in all kind of reporting all the time, that you group by year, by quarter, by week, and in this kind of hierarchical way or similar. So here I'm gonna bring back our manager ID, and use that. Yeah. Again, recognize the order of these things is completely up to you. Only of course quite often or quite commonly you will do that you output your criteria that are your grouping criteria first in that order, and then the consolidation. But there is really no requirement for that. It is just it works quite well for us as human beings to be able to read that. And there you go. So now we have our manager ID. And you see now, of course, our manager ID 5 cuts into 2 subgroups. So that way you can build these hierarchical reports, and you see, of course, by default it repeats your grouping criteria. There is no default functionality in SQL to omit that. So there is all kind of queries out on the internet if you're interested about that, how you can kind of fiddle that it looks like that if you insist on that you don't want to see the 5 again. To me that is rather pointless, because most of the time you're gonna output these data in your front-end application, and it's much easier to do it there than do it in the query. So there we have our multi-level query. And now the last thing, of course, we can do here as well, with the same warning I've given at the time when we've talked about multiple consolidations, is we can of course use multiple consolidations, but remember again that these multiple consolidations are individual, each on their own. So if, for example, I put in a min date of birth and a max date of birth, then that is rather obvious that of course these come from separate records within that group, and that example quite nicely demonstrates what we are up to. So what we are basically expressing in that report is grouped by manager ID, within the manager ID by initial, we say how many people do we have in that group, and what's the youngest and what's the oldest. No, the other way around. What's the oldest and what's the youngest person in that group? And that is a sensible report, but that goes back to the point made earlier. When you use consolidations, be sure that you understand what you're actually consolidating. If you understand that, these grouping criteria are a very powerful tool. Well, and that's really our group by clause. There's a few additional things you can do around it, and we'll cover that in a separate lesson. Let's talk about the having clause now that comes with the group by clause. So we're going to start out again from our select star from person that you see down here, and when we learned about group by, we created a group by clause like this. So if I execute that, you see what that gives us is the count per manager ID that we have in that person table. Now there's a few things we can do with the having clause, and the having clause essentially really is the where clause for the group by. So pretty much all the things that apply to where clauses elsewhere in your SQL queries apply to the having clause. So the having clause filters your groups by certain criteria. So for example, here you could say I want to filter on those groups that actually have a valid manager ID, or I want to filter on those that have a certain count. So let's do this. I'm going to start with the count. So I could, for example, say count larger 1. So I only want to see those groups where my output in this count column is more than 1. And quite often you do this, that you say I'm really not interested with groups that only report on one record or on no records whatsoever. Yeah, you want to if you do these kind of groupings on sales, for example, you're typically not interested on things that have no sales, or you may just the other way around be interested in only those products that don't sell at all. So there's a lot of these scenarios Here you could, for example, say I'm interested on the managers that don't have any people assigned to them, which we don't have here in this database model. So we're going to look at this version of having account larger 1, just to give it an example. And you see then this output reduces to that one line because the other two were ones. One thing which of course is a bit unpleasant here is now that we have the consolidation twice in here. And again, what we can do here is we can use an alias to do this. And we could, for example, call that direct reports. And then we stick that one down here. And as you would expect, it still works that way. Now then, go back to the unfiltered group. The other thing you may want to do is filter on groups which actually have a manager ID. So you would use a not null, and that way filter on that one. Oops. So there we go. Now that null line is disappeared there. So that way we can filter out, and of course we can do that the other way around. And then we see we only get that one. Right, and of course also what we can do here is similar like in a where clause, we can have multiple aspects to it. So I could still say direct reports larger 1. Now again, if we first run that part, you see then we have these two ones. We have the manager ID 4 and 5, and now if we add this part to it, you see that one line disappears because now we also filter on the direct reports. So there you have your having clause. So really the kind to remember what the having clause is all about is the having clause to the group by is like the where to the select. It allows you to filter groups by various criteria as you see fit in your query. Time to talk about some do's and don'ts again, this time do's and don'ts on grouping. We've talked about do's and don'ts in consolidating in a separate lesson, and at that point I already said there is similarities to that in grouping, but we get additional ideas around do's and don'ts in grouping, so we want to look at that now. Basically what we have said earlier in consolidation was that once you start consolidating, you need to consolidate all criteria. So you can't mix consolidated and unconsolidated columns in your select clause. And that as such remains true. The difference now is that of course in a grouping criteria that rule gets extended by the exception that of course your grouping criteria itself is not consolidated and it can't be consolidated. So in the grouping scenario it gets slightly a little bit more complicated in that the rule is all grouping criteria are unconsolidated and need to be unconsolidated, and all other columns you output need to be consolidated. And we can see this in that example. So we have our person table again, and then we have this group by clause we've used elsewhere. And you see we group by the manager ID, we output the manager ID, of course non-consolidated, and we consolidate all the other bits, our count, our minute max, date of birth, with again of course the reminder all three consolidations are independent of each other and they are not linking to a particular record. So if we do that, then of course we see our output. Now if I was going to try to violate that rule by, for example, putting in a min manager ID here, then again as elsewhere it may well work, but it actually doesn't create the right thing. And you see it actually does here, and it by chance creates the right idea, but remember that is actually not accurate. There we go. So that is the right way to do. And again, in some database systems the database will just plainly refuse that query if you do this. The same goes if I reduce this one to date of birth, where MySQL unfortunately is a bit tolerant on that. It will do this, but don't be fooled, it gives you the wrong data, and you can tell by the fact if you memorize these data here, obviously when it's only one, well, yeah, you get away with it. If you have here the min and max, you see you have a 1970 and a 1990, and we run that now, you see that creates something rather peculiar, which looks like an average or something like that, but certainly not what we wanted. So again, if I undo that quickly and run it again, you see then we get some sensible data there. The same goes of course if I reuse our earlier example by grouping by a second criteria, by for example using the initial, the first character of our first name, then this as such, if I run it like that, is wrong, and in many systems it will fail. Unfortunately here it does, but it creates again something which is not necessarily right. By accident here it is right. Really what I wanted to do here is that I wanted to use the initial as a second grouping criteria, and run that. And you see it actually creates a different output then. So that's where it can become slightly a little bit messy, unfortunately, because there is in recent years a notion for many database systems to become more fault tolerant. Unfortunately, these higher fault tolerant often enough comes at a price, and that's where I'm not overly fond of it, because it lures you into the impression everything's fine when actually it isn't, as you can see on these examples. So there we have a couple of these do's and don'ts again. So remember the base rule for grouping. Grouping criteria are never consolidated, they always go into your select clause unconsolidated, everything else always goes in consolidated. Then you know you get the right output and your query result is reliable. Let's talk about table aliases a bit. Table aliases are an important feature when it comes to joining different tables. They are not really relevant if you only have one table, but once you work with multiple tables, as often you will do, and you join them, they become very handy. We've talked about column aliases before, which have the idea of giving a column, especially a calculated column, a sensible, easy readable name. The table aliases have a slightly different idea. It's similarly an idea of simplifying, but with a different focus. When you work with multiple tables, you very quickly have to repeat table names over and over again because you have conflicting column names and the like, and you want to abbreviate this. So the table alias typically comes in to abbreviate this. Let's look at a very basic join here. Have a quick look on our diagram. So we have, for example, our person table and we have our contact table, and you see that person ID and the contact PID is our relationship. So we have our person table here as usual, and then we have our contact table. And you see there we have all our mapping. And of course, if we are doing a very simple join now, we would do a select star, and I'm going to break that over because it's a bit easier than to read as it gets a bit longer now. So we're going to join person and contact, and we're going to use a basic where clause to resolve that relationship. So we have the person ID equals the contact PID. Now if we run that, we see now we get all our persons with their contact details. In the end, if you look at this query, it wouldn't necessarily need the table prefixing because you don't have conflicting names. At the same time, it makes it of course more readable because you know what belongs where. But of course it means you repeat your table names over and over again, and as you can see on this diagram, there's a few table names that get rather long, and that is still short compared to what you find in many database schema. So it's really becoming a typing hell, and in particular, of course, you will mistype all the time. So what I'm going to do here is I'm going to modify that and introduce table aliases, which really have the purpose here of abbreviating the whole thing. So it is pretty common to just use one or two characters for these table aliases. And of course you would do the obvious, you abbreviate person with P, and you abbreviate contact with C. And now you can go by and reduce this part here to the aliases. So you see your code gets significantly shorter and easier to maintain, and once you are in this kind of table aliasing, it also becomes very easy to read. Now if I execute that, you see it still of course returns the same output. Right, and also what I can do now of course is I can be more distinct in my query I want to do. For example, I want to say I only want to see the first name and the last name, and I want to see the actual value here, the actual detail. So I'm going to say p dot first name and p dot last name, and then I'm going to say c dot value. And now I run that, you see I get my list with information that actually from a user point of view are the interesting bits in there. Again, strictly spoken, you wouldn't need that, but if you consider building these things up further in complexity, it's obviously that it's helpful to have these table aliases prefixed there, so it just becomes a bit more understandable what comes from where to where. A side remark to make here is that unlike here where you see it just outputs the column name, in some database systems, if you use these aliasing, it will actually introduce the alias prefix into the column names, which, especially if you use that from a application language, will probably cause you a bit havoc. If you have that, of course, you can easily avoid that problem by again putting a column alias in here, like for example here I would put something like contact number or something like that, whatever I fancy there, and would run that, and you see then I get that. But I said that is a feature only for certain databases, that they actually output these alias prefixes in there. Normally it's quite easy to work like that, and it's very helpful, and we're going to use that when we do our various concoctions of joins a lot, because it just eases the typing pain a lot. So that is the table aliases as a very handy feature of abbreviating your select statement with multiple tables. Now it's time to talk about inner joins, probably the most important feature in SQL as such. If we're going back to our database schema here, we've talked about that we have a whole group of tables there that are all related to each other through these relationship lines, and while of course the structure as that is great for storing your data in a database, very efficient, of course in your reporting scenario, in your output scenario, when you want to see the data in your application, you need to reconcile them and join them together again, as it's called in databases. So we're going to learn about that, and we're going to start here by joining two tables, and in a later session we will look at how you join more than two tables, which is really a continuation of that. So understanding the principles how you join two tables really gives you the tool on hand to take it further from there. So what we're going to do is we're going to join the person table and the contact table. Now, and as you can see in the highlighting here, the relationship sits between the PID and on the contact side and the ID on the person side, and it also sits between the CT ID on the contact and that further table contact type, which has again a primary key ID in there. So we're going to use the relationship between person and contact. So that is expressed through the primary key ID on the person side and the foreign key PID on the contact side. Right, let's go back into our editor, and of course we see first of all here we have our person table, and here we have our contact table where we have the actual contact details, and then we have the keys linking them together. So how do we do such a inner join, which is really the most basic version of a join? We start of course with a select star. Because things get more complex, I'm really going to use the more broken over writing. So you put the select in one line, the where in another line, the from in another line, and so on, to make it a bit more readable. So for the inner join, I'm going to start with the so-called implicit version, which is my preferred version for the inner join, because it's just easier and straightforward as far as I'm concerned. I show you the explicit afterwards as well. In the implicit join, you simply extend your from clause now by having a comma-separated list of tables that you want to join. So here we want to join person and contact. Now, that alone is a workable statement, but not a particular sensible one. I run that quickly, and you see it creates a whole lot of outputs. And you see, interestingly here, it pairs every single person with every single record in that contact table. And that's exactly the pitfall. That's not what we want. Of course, we want to see the contact details to each person. So that's an interesting observation to make here. If you just do a join like that without anything else, it creates what's known as a cross join. And some database systems actually celebrate this as a feature, which I've never quite understood, because I've never come across a situation where I really would have a sensible use of that. Basically what it means in that cross join, it combines each record on the one side with each record on the other side, so you get all possible permutations. Mathematically that's quite an interesting feature, but in real life, as far as I'm concerned, it's not. You easily fall into that trap by forgetting something, what I will show you next, how you actually team up the right information. And you can always see when you've accidentally built a cross join, see that by looking at the output, and you get these interesting repetitive blocks here. So if I scroll down, you see there's always these kind of blocks of 6 on this occasion, because we have 6 people in our person table. And if you see something like this, you should always become suspicious, because that probably wasn't what you wanted. And that's a typical sign of a cross join, that you get these repetitive pattern showing up there. So how do we get from a cross join to a proper inner join as we want it? Well, actually quite simple. We add a where clause, which now brings together the right records by basically filtering them out. And if we look on this output here, we can of course kind of make that out, how that works. What we really want to see is those records where the ID here, which is the person ID, equals the PID on contact. So you see we have Joe Blocks, yeah, that's fine. We don't want to see these ones, yeah, then 2 to 6. In the second one, we don't want to see number 1, because that is actually not belonging to number 1. No, it actually does here. So we want to see that one as well. If we go further down and we come to the second person, obviously we don't want to see this line, because that belongs to the first person, not to the second. But we want to see this one, and we don't want to see the rest. So what we need to express here as a where clause, and that is exactly how you build an inner join, is you build in that where clause comparing these two values. So we say person.id equals contact.pid. Now if we run that one, we're going to see we get a much more sensible output. So we get the 2 things for Joe Blocks, we get a couple of things for Paul Miller, because there's obviously a few more things put into the database, and so on and so on. And we get actually the kind of records that we want to see here. And you see on each one, if you look over it, you see it's the right kind of people you see there. So that way we've created our inner join, which is really the kind of information we want to see, that for each person we see their respective contact details. Now obviously we've talked before about table aliases, and of course that's the thing I'm going to use here now, because it just makes it so much less typing. So I'm going to use the P for the person, the C for the contact, and gonna reduce that here. And you see it still works, it still does the same output. Now of course I can filter that down in my select statement, in my select clause, onto what I really want to see. Say I want to see the first name, I want to see the last name, I want to see the date of birth, and I want to see the value, the last column, this one here. So if I run this, and I've obviously just mistyped something, let's go back and see what I've done. So what I've missed here is the R in first name. And you see, then we get our output. Right, so there we have our list, and you see again that is that idea that I can build the different bits I've learned on the different aspects of my SQL query, on the different clauses I can build together in here. Like for example, now I can put in an order by and say I want to order that by last name. Prefix it with a table so we're sure what we're meaning. Not necessarily required, but always better. So I want to sort that by last name ascending. And for example, I could sort that now, if I have a quick look over here, by my CT ID, which is basically, as I don't have anything else, may give me a ordering criteria for my different contact types. So you see again, of course, I can use something that I don't even have in my select to apply a sorting order. Right, and if I do that, then I get my list. And of course I can do normal filtering on that, like I can do again my beloved filtering on the initial, and say I only want to see those with a first name starting on J. Here we go, and now I've reduced that list further. So as before, we can build all these bits and bobs together to use in our inner join, just as we've done it on where clauses elsewhere. Okay, now also let me show you the explicit inner join. So I'm going to take all that out here and start from new. So, and we're just going to use the basic version, not bother with all the other bits. Of course you can do them all here just the same. So we have our from clause, and unlike in the implicit inner join, you don't have a comma separated list here now, but you only put the first table in, but I'm going to use the alias again, and then you say inner join and put your second table, which is of course our contact table, And then you have a on clause here as well, which includes your joining condition. So basically what we had in the where clause. So we're going to say PID equals C PID. And that is our explicit join. Now if I execute that, you see there we have again our data pulled together as we've seen them when we started with the inner join. One advantage of the explicit version, admittedly, here is that you're less likely to forget your join clause, because the database won't let you away with if your inner join on is not complete. But in many ways it's a much more lengthy way to write it, and we're going to see the explicit version back at a later stage when we talk about outer joins, because that's where they become handy and much more sensible than the implicit way. But for the usual inner joins I tend to use the implicit way because I just find it so much easier to code. But then in the end it's up to anyone else what your preference is. And so I'm showing you both versions here, as obviously when you read other people's scripts you will probably come across the one as the other. Okay, and that is basically our inner joins. So we've seen how you build your inner joins in the implicit or in the explicit way, and how you combine this joining again with all the other aspects we've already learned elsewhere to create quite sophisticated queries. In this lesson we want to talk about outer joins. Just like the inner joins, outer joins allow you to consolidate data from multiple tables related to each other into one big report, bringing back together these related data in a way that they are actually readable for the user. So what's the difference between inner joins and outer joins? Inner joins only show you those records where all elements are present, where outer joins show you also incomplete records. What do I mean by that? If we look at an example, here we have the person table and we have the project person table. If we're going to do a join about that, what we're basically are going to see is the persons and their involvement in projects. So to what project is a person assigned and what role does it have within that project. Now if we're going to do a join between person and person project, in an inner join we would only see those persons who are assigned to at least one project. Whereas in an outer join we're actually going to see all persons regardless whether they are assigned to any project or not. So the outer joins are great to identify these kind of gaps you have in a database. Like on this occasion, the person that is not assigned to any project. Why do you have a person on a database like this when it's not assigned to any project? Equally the other way around, if you look from the project to the project person, you would be able with an outer join to find out projects that don't have any people assigned. That's strange as well, unless it's a project that's only just started and you're yet to assign people. Similar with a role. So you find a lot of these scenarios where in the end you want to find data in your database that are kind of without sense in there, that are not used at all. And quite often that points to either some malfunction somewhere or to some legacy data that you really want to get rid of. So let's do that, go back to our editor. So again, we have our 3 tables that we've just been looking at. We are gonna use here. So the person, the project person, and the project. And of course, again, we are starting here with outer joins over 2 tables. And of course, you can expand that to more tables. Once you've got the understanding of the outer join between 2 tables, you can do this with more tables. And we're going to look at that at a separate lesson because there is a few trickinesses to it. Right, so how do we do our outer join? First of all, for the outer join, I would strongly recommend the explicit way of doing that. You may recall from the inner join there's an implicit and an explicit version. There is an implicit version for the outer joins as well, but it's not even supported throughout, and it looks rather messy. So for the outer joins I will use the explicit version, and I'm actually ignore the implicit version here. So what we're going to do is a select star, of course, from, and then we start with the first table again. So that would be person on this occasion. Now I'm going to start with a conventional inner join, so we see the difference between both. So we want to join person and person, project person, it's called. You see, one of the typical things that happens always, and that's why you want to have these diagrams on hand. You start having so many tables in a database that you get mixed up with names. So having something where you can look back is always helpful. So on, and now for example, if I can't remember my keys, I'm just going to look. So I have obviously here the person ID, and the respective to that one is on the project person, the PID. So on, actually I should of course do my aliases here again. So I'm going to use a P for the person and a PP for the project person. You are quite free to use whatever aliases you want here, of course, but I tend to do it that way. So we say on p.id equals pp. And again, we've just said it's called PID here. So .PID. Right, if I run that, then I'm going to see our inner join that we are already used to. Now you see we have persons 1, 2, 3, 4, 5 on here, and you may recall from earlier that we actually have 6 persons. So we obviously have one person here that's not assigned to a project. Now that's where our outer join comes in, and we're going to use here what's called a left join. I come back to that in a second. Now if we run that one again, you see suddenly we have one record more. Now we have Susan Baker in here, who is not assigned to any project. That's why she doesn't show up in the inner join. So that really is the purpose of your outer join. And of course now you can do your usual by adding additional where clauses. So for example, if you're actually looking for those kind of orphaned records, like the person that isn't assigned to any project, you're probably gonna want to filter on exactly that situation. So you're gonna say you filter on the nulls here. So obviously on this occasion, though you can use any of these 3 columns, you would probably use the one that you're referring here anyway. So you would say PID is null. And again, if I run that again, and you see now we only have that one record. The thing you nicely see here as well now is that when we're talking about outer joins, you're actually eventually get to a situation where these key values, the primary key and the foreign key in a relationship you used to match up, actually becomes different. In an inner join, it never matters whether you would filter on the ID or on the PID over here, because it always would be the same. On an outer join, of course, it matters, because that is where your gap is. So here it's important to use the pp.pid to filter on. So that is our outer join in the first version, which is called a left join. So what's the difference between a left join and other outer joins? First of all, there is a left join and a right join, and in some database systems, though not here in MySQL, there's also a full join. So there's nothing like an outer join as such. The outer join comes in these three flavors. And basically what the left and right simply expresses is that it is the side which is the mandatory side and which the other side is the optional side. So the left join basically means we're going to include all persons, because that is the table sitting on the left of our join, and we allow therefore for null values on the right side of the join. So you could just simply turn around that join now, and then you have a right join. All I need to do is swap around things here. So I make that the project person, and of course put the alias the other way around, and I take the project out here, and I make the left a right, and then I can run that again, and you see we have the same output. The only difference is now the columns are the other way around, simply because of the select star, of course, arranging the columns just as the tables are sitting. So in the end, the left join and the right join creates the same result if you just swap the tables around. And in the end, it's up to your personal preference which way around you do it. There is no rule for that. I tend to generally, when I do joins, work along these relationships, because it just means you keep up with what's going on. If you start mixing around your tables, you lose track what you're actually joining with what. So in that occasion, because I've done person and project person, the left join just came in handy. If I'm going to do project person and project, I may just as well go for a right join, and that's exactly what I'm going to do here next now. So we're going to do a right join on project. Oops, one P too much. And I'm going to call that PR, to see if we have projects that have nobody assigned to. So again, then I need to look. My project has the ID as a primary key again, and here we have the PR ID as a foreign key, as you can see there. So we are in the PP, the project person table, and we have the PR ID, and then I've said I want to use the project ID, and I'm just gonna skip that where clause. Right, and now I can run that, and you see, in fact, there we have one project that has nobody assigned to it yet. So you see there you have another example of the right join, and again I could just flick that around to a left join now, and I would be fine. Sometimes it's just a matter how you want to output it. This kind of right join output sometimes may just be a bit unhandy and a bit silly looking, but on the other hand, most of the times you don't plot these things straight on the screen. You use it in your application, and the application then does the visualization, so it doesn't really matter. As said, there's also something called a full join, which doesn't really make sense on a one-to-n relationship, because as you probably might guess, the full join is a combination of left and right join. So it really only makes sense when you join at least 3 tables, in particular these kind of m-to-n relationship table lines, where then you can actually have the kind of open ends on both sides. So if you were going to do on this schema something like the person, the project table and the project table, then you would be able to say, well, I want with a full join I can see all the persons that are not part of any project, and I see all the projects that don't have any person assigned to it. As said, MySQL doesn't support that feature, at least yet, but you find that in SQL Server and in Oracle. So if you're in need of that, have a look at that. The warning sign has to be, the more complex these outer joins get, the more careful you should be and really test that very thoroughly, because you easily include or exclude data wrongly that actually you didn't want to see or you wanted to see. But used in the right way, the outer joins are a very, very powerful feature. In this lesson we want to talk about self-joins. Self-joins are inner or outer joins, but unlike normal inner or outer joins where you join 2 or more tables with each other, in a self-join you join a table with itself. Now, what's the purpose of that? Here we see an example, our person table, which we've used various times already, which includes such a scenario where a self-join comes in handy. We've used this manager ID column on various occasions already, and basically what it does, it refers to another record in this table identifying the manager of that person. So we see we have a whole range of people who all report to the ID 5, which is Rick Walker, the CEO of the company. And then we have here one record that reports to the manager ID 4, which is Jenny James, who herself then reports to Rick Walker again. And of course we have Rick Walker, who doesn't report to anyone because he is the CEO. So obviously there's various scenarios where you would want to plot out a report that shows people filtered by all kind of criteria, but who also you want to show the manager to that person. And of course you don't want to show the manager ID, you want to show the name of the manager, and that's where the self-join comes in. So how we're doing that? We are starting off again with our normal select star from, and just as in every other join, we mention the tables we want to join, which is person and person. Now, and here you see an example where no way you can avoid using table aliases, because obviously once we do our where clause for the join now, we need to be able to identify which of the two person table instances we're meaning. So we're going to call the one P and the other M for manager, and then we build our where clause, which is now of course linking the primary key to the manager ID. So what we want to do here is we want to link the P manager ID to the manager table ID. So that way we join the two tables with each other, the same table with itself, and we're going to filter on these combinations where we see the manager joined to it on this manager ID criterion. So if we run that, then we see now we get this table here, and you see here we have our people with all the columns from the person table, and then we get the second block, which is the joined manager table, which of course is the person table. And now we see we have Rick Walker and Jenny James on here. And of course in practical terms you will typically filter that down on the columns you want to see. Like for example you would say P, again we need to be specific about the column names now of course, and you want to see P last name and take our date of birth as we so often had that, and then you want to see the manager name to it. And if we run that again, you see then we get of course a much more consolidated list. And of course you probably would do in practical terms often something like that, that you would concatenate the names as we've done on other occasions. Now one wee gap you see in here is that obviously Rick Walker doesn't show up in here itself, because we're doing an inner join here and he has no manager assigned to him. Obviously he doesn't show up here. So if we want to have him part of that, we're going to need to use an outer join for that. So I'm going to modify that and show you of course that you can do an outer join on a self-joined scenario. So we're going to do a left join, because the left side is the table with all our stuff. And you see here, by the way, how nicely you can convert an implicit into an explicit join by just maneuvering the keywords around. So we're going to join that on the manager table and then of course have our same filter condition as before. And if we run that, you see now we have Rick Walker in here as well. And now, by the way, you may want to order that output, say by manager last name ascending, just for talking sake. And we run that again, and you see now we get our list here in a way where we see of course Rick Walker as the top guy, because we have sorted on the manager last name. He doesn't have one, so he comes first, and then we get the rest. So there you have your self join, and that's really all that is to self joins. The main obstacle with getting to grips to self joins is really getting your brains around it, because that idea of joining a table with itself is something that is a bit tricky to imagine in your brain in the first instance. But in the end, just think about it as if it would be two tables who just happen to be the same, which you join, and then you just apply the same logic as you do for other joins. And then you can make use of these self-joins, which in many occasions are quite a handy feature actually, especially when you have these kind of hierarchical scenarios in a database. In this lesson we want to have a go at some more complex joins, we'll say over more tables and so on. Obviously we're going to do inner joins just as well as outer joins, and the higher level of complexity in particular comes in when we come to the outer joins. So first of all we're going to look at some inner joins. And what we're going to do is we're going to extend our inner joins beyond two tables, like we've done things like person and contact and so on. And now we want to extend that in the first instance to three tables, but then we're going to grow that further to see the idea how you do these complex joins. The one thing I always recommend is to build your joins along these relationship lines. If you don't, you very easily get lost and your SQL statements become messy and very difficult to evaluate that they actually do what you set out to do. If you do these kind of things, you're very easy end with cross joins and the likes, so the data you're outputting from your query is actually not what you wanted to see. And often enough that can be very difficult to spot actually. Data appear to look fine, and when you look closer they are actually not. So being a bit structured and organized in these respects is helpful because it avoids errors. So I'm going to start with a inner join over these three tables here on that side and show you how that works. So obviously our starting point is our person table as usual, and again because it gets a bit more complex here I'm gonna add a bit to it. So obviously the first table to join is the contact table, which we've done elsewhere already, so we're going to start with that, and of course I'm going to use table aliases here again. Right, and we've said before for these implicit joins we need a where clause that links our two tables together, which, to remind us, is here when we go into this relationship, the ID in person and the PID in contact. So p.id equals c.pid. Right, and then we're gonna test that query to see if that does what it wants. Yeah. And we see there we have that next table worked in there now. It's another thing to remember, and I always suggest, is don't build these complex joins in one shot. Build them step by step and test them and see that actually the data you're getting out of there are right. And here you can quite easily tell we have for the different people the different sets of contact data, and you can follow up the keys and see that it all filters fine, so that's okay. So that's the first two tables joined together, and now we want to join the third table, which is our contact type. And you see there we have the ID again, a contact type, and we have a CT ID in contact. So what we're going to do there now is we're going to add the contact type here, and we call that CT. And now the trick you need to do here is to join that third table in, is you need to add to your where clause. So we have an end, and now we build just as we do the where clause for the first relationship, you build a where clause for the second relationship. So that is then c.ct ID equals ct.id. So what you've seen, what I've done here is I go first of all along this line from person to contact type, person, contact, contact type, And then I build my where clauses exactly along the same way. I do the relationship between person and contact, and then I do the relationship between contact and contact type. And that way you have a very structured statement which you can easily evaluate to make sure that you haven't missed anything. So that way you get your join over 3 tables, and you see the base rule, easy to remember here, is always you have one less join conditions than you have tables. So you have n-1 join conditions. You have 3 tables, so it's 2 join conditions. And now you can probably already guess, when we go further, if you add more tables to that, you add with every single relationship another where clause. So if you have 5 tables, you need to have 4 where conditions. If you don't, then you've obviously missed something. Right, let's have a shot at that and execute that, and you see now our table gets a little bit larger, and there's not much to it. We've added these 2 columns to the right. Of course, now we will probably start to filter down on the columns we really want to see, but again, it's always helpful in the first instance to work with the select star, so you see all data and you can reassure yourself that you got the right data. Also, of course, as usual, we can add here a normal where clause, which is not a join clause. So we could again do our regularly used initial functionality, only getting those with the first name on J. And if I do this, you see our list goes much shorter. So that goes, of course, the same as everywhere else. Again, that we can just do these kind of things. Now we're just gonna add more to it now, and we're going to go back to our diagram to see what we have. So now next I want to add in the project person and the project to it. So, and along that idea what I've just said, I line them up in the order as they sit in my diagram. I'm gonna add that here at the front. So we have project and we have so we're adding from that end, and then we have project person. Project person. Now that becomes a PP, and my project we call PR. Now, of course, in the same way, I'm gonna move that around here now and add my previous ones here. So we have PR. Let's see, in PR we have the ID, and we have on project person we have the PR ID. So that's what we need to match here. So P equals pp.PR ID. And then we go from project person to person. So there we have the PID in project person, and we have the ID in person. So PID equals PID. And you see that queue just nicely builds up now. So we have 1, 2, 3, 4, 5 tables, and we have 1, 2, 3, 4 join conditions. So we are fine. And of course you see now our output gets a bit wider, more than actually fits in the screen here, just about more. And now you can work on. One thing you see in here now is we start to get all kind of duplicated columns. So for a kind of sensible output, also an output that you can use in your web application, you will need to use label column aliases now. Like for example, we have that column called label a couple of times. We have a label for the project, we have a label for the contact type, and if we were to add the role as well, we would have another label. So these things you now will have to reduce and make sure that you have something straightforward. So I'm going to do this with a few of these things. So we're going to have PR label here. So, and I'm going to call that project name, because that's what it is. But of course don't have a space in here. Then we're going to have the budget, of course. PR budget. We certainly want to see that one. Then we want to see probably the first name and the last name of the person involved. So that is P first name, P last name. We may not be interested in the rest of it, but then we certainly want to see the contact details we've been plotting out here. And again, we probably want to see first the label and then the value, so we swap that around now. And we say we take the value which comes from CT. No, the value comes from C and the label comes from CT. So we have C dot value, and again that would get properly a name, so contact detail, for example. And then we would have, and now I've just done it the wrong way around. We said we wanted to have first the label, which would be the contact type, for example. So you see, this way we've built us a bit more useful query. So I'm going to run that now. And you see, then we have a nice, much more consolidated list. And what we see now is we have our projects with their budgets, we have the people involved in that project, and the only thing that's missing yet is the role. So now we could go by and say we also add the role to it. Well, we're just gonna leave it there. I think we've seen the principle in the various forms now, so adding yet another table should be reasonably straightforward. We're gonna head on to looking at the more complex outer joins. So I'm gonna wipe all that out, and we do a similar thing now with an outer join. Quick look back on here. We're going to do again that line project, project person, and person here. So we start, of course, with the project. Don't forget the from. And we do a left join project person on. Don't forget our aliases, else we type our fingers off. PR ID equals PP PR ID. So again, start step by step, and you see now there we got our projects with our persons in there. Now, extending that to more than two tables, similar like with the inner join, goes here the same by adding on the same structure. So you may just add the next join here. One thing though I would recommend is to properly express yourself with brackets again what you actually want to do, because else you may find that again the database interprets it in a different way from what you wanted. So we've started here with joining project with project person. So we are gonna add to that now by joining another one. Remember, because we do an outer join and we have these loose ends in there, the order how you join may well be of interest. So before you matter your brain, just make sure you put some braces in there, then you know it actually is the way you're thinking of it. Now you may be tempted here at that point, when we add the person to it, to do an inner join. However, if you try to do that, we're going to see that actually doesn't do what you expect it to do. So on PID equals, what my alias again, P for person equal PID. And by the way, don't forget to close the bracket. Now you see at the moment we see here the project with all these people, and we have in particular our unused project, our unassigned project down here. So obviously when we add another table we want to see more additional information, but we want to see these open ends. Now if I run this one, you see our Google Plus project has just disappeared. That tells you that this inner join actually isn't doing the trick as you thought, because the database optimizes things. So really what you normally have to do is, once you start with outer joins, you need to stick to outer joins, and the easiest is to do these queues in a way of left joins throughout, as I've just changed here. So we're going to do that, and you see now we indeed have our additional columns here. And that's where you, by the way, see the point. If you were able to do a full join, which as I said doesn't work on here, you could actually also see people who are not assigned to any project. And to just give it another play here, I'm going to change that to a right join, and you see it's not going to do the trick you want. You see our Google Plus has disappeared, and now we have Susan Baker, who's not part of any project. But that's not really what we want to see here. So that's an example where full joins come in. As said, MySQL doesn't support that yet. So you see there is ways of mixing left and right joins, but it tends to be rather tricky, and there's very few sensible occasions where you really would mix left and right joins. Typically you do all left or all right, or you do an all full if you have that on your database system. But that's really what you do. So again, be very careful when you do these kind of things to very carefully double check that the data you get are actually the data you expect, and more importantly are the data that are in the database. It's very easily with these outer joins to be fooled, and I've had the one or other unpleasant pitfall over the years in projects where something went wrong with outer joins and we didn't realize, and only in a late testing stage we found that, oops, we're missing some data here. So that is your complex join conditions, and again you see the same here with our outer join. Once you've got the principle of it, of course you can drag that on into as many tables as you want, with as many extra criteria on it, and so on and so on, and build very complex queries there. In this lesson we want to find out how to use subqueries as a filter condition. What is a subquery, first of all? A subquery is a second query you build into your main query. So the subquery is just as much, in most cases, a valid query in its own right, but it contributes some aspect to your main query. For example, it creates a dynamic value in a where clause. And that is exactly one of the typical scenarios where you use subqueries. So, for example, if we look at our select star from person again, which we see here, the output of that table, we could, for example, say we want to, out of that table, we would want to see the person, the oldest person or the youngest person. Now, there's no way we can do that in one query. We can, of course, do something like a max date of birth, and of course that will give us the youngest person in the system. But of course, as we've said before, we can't combine that with outputting other details about that person. If we want to do that, we need to build this max thing as a subquery in there. So what we're going to do is we're going to stick another query around that then allows us to output the details about that information. So that would go back to our select star from person, where, and now of course we would need to look what we want to do. We want to basically get the person, or strictly spoken the persons, with the maximum date of birth, so the youngest persons. Of course, because we work set based in SQL, in theory we could have more than one person on the same birthday, which is another hint why these kind of queries just don't work in one go, because mentally we may think we're looking for one record, but actually if we think about it carefully we will find out it's more than one record. So what we're going to do is we're going to stick in a filter which checks on the date of birth being equal to that maximum date of birth we distill in our subquery. And again, though not necessarily required, but good practice is to just put a pair of brackets around it. That way you are sure that you know what you get. Now again, we can test this quite nicely in components. We've already done the max, so that is the 1990 birthday. So now we can go by and just execute that line and can see who that is. 1990, that is Jenny Palmer, we expect that. So we actually only have one hit here, but of course we could have more. Now then we can run the full query, and there we go. So there we have our youngest team member basically put out with that query. And these kind of scenarios are a very common example for subqueries, where you dynamically need to create a where clause, and you need a value in your where clause which is not directly in your underlying table you're querying, but is distilled from something else. I could do a similar thing now and, for example, say I want to see all those people that are younger or older than the average. So I could change that in an average. And obviously the equal wouldn't create anything, because the chances that we have one person which sits exactly on the average is highly unlikely. But of course we could say we are looking for those younger, so their date of birth would be after the average. And now we can run that again, and you see there we get two people. if we want to be sure that we done the right thing, of course we can test the subquery. But also I'm going to do the other way around now first. So we're going to do the guys older than the average. So we have 2 under the average. So because we have 6 people in there, we would assume that we find some 4 on the other side of the query. We're actually only getting 3 because actually if we look back into the first, we find there is one that doesn't have a date of birth. So that makes sense. Yeah? So again, that strategy makes sure that you test these things properly. So I'm going to take that subquery out here and run that individually just to be sure that that does what I want. And you see that of course gives some funny number. One of the tricks you can do is you can stick that in a date and that converts it into a proper date. And you see then we get our average date. So the average date of all the birthdays we have in there is the 14th of July 75. Yeah, and always remember to do these tests. Don't trust yourself, don't trust your own cleverness. I can tell you how often I've hit the wall with that. So better safe than sorry. Test the components in such a subquery. So in this kind of scenario, of course, you can use in all kind of operations. Obviously in that subquery you can put whatever you want. So everything we've learned so far in our other lessons about the select query you can use there. And of course it can come from different tables and so on, as long as the output matches. So on this occasion where we do such a kind of equal, smaller, larger comparison, you need to make sure that your subquery creates exactly one value. That's also known as a Scala subquery. So if this one, for example, wouldn't be an average, for example, you would just say I select the date of birth, yeah, which basically creates you a 1-column table of dates of birth, then this query shouldn't work. Again, you find some database systems being a bit more tolerant these days, but the same as elsewhere, this tolerance normally goes wrong. So if I do this, you see the query actually gets stuck. So it's an invalid query. So it's important to always look out for this scenario where you build subqueries that the data types you work with are fitting. So if you need a Scala value, you need to have a Scala subquery. And in the end, you also need to make sure that, of course, the kind of data, the data type, whether it's a date, whether it's a string, whether it's a number, are fitting. Else you're gonna get all kind of interesting effects, because in certain areas the database may just convert things, but the chances are it doesn't actually convert as you would like to. Right, so that is our first variation. The second variation is to exactly drill that idea further, that you may actually have a non-Scala subquery, and that's where your in clause comes in. We've mentioned before. Now the in clause allows you to actually check against a list, and for example we could say we want to check the ID. So we want to filter on a sublist of IDs which typically will come from another table. And that is where the in clause becomes interesting. Of course you find in clauses where you have a hard-coded list, but that normally points to maybe your database design not being quite as great as you wanted. Now we want to create a subquery here which is dynamic, and I'm going to have a quick look over on our diagram. So we're on the person table, and you see in the project person table we have, for example, the role, and now we could go by and say we want to have all those persons in the person table that actually fulfill a certain role in whatever project, which is that RID. So I give us a quick insight here into that role table. Select star from role. And there we go, we have 4 roles. And equally then we can have a quick sneak peek on the other table we're gonna use actually, which is the project person. So, and there you see we have various people in the different roles, so we can almost pick whatever one we like and that way build our subquery, which we're going to do here now. Again, if you can, build your subquery beforehand to make sure it creates the right data. So we've said we want to filter on a certain row ID, so where RID equals, and let's say we take 4. Now if we run that, you see we return 3 people, and here we have the person ID, which is our primary key in person. So we have 2, 3 and 4 returned. So now I can copy paste that thingy in here, and the kind of structural bit is relatively up to you. I sometimes do it this way, sometimes do it that way, and quite often I just tend to indent that subquery. SQL doesn't mind that at all. It's of no relevance how you indent things like that. But now you see we have here our select star from person, where we filter on the ID in person to be in this list that this subquery returns. Now if you try that, you will again find that won't work yet. It crashes. Why does it crash? Because we're checking on the primary key, on the ID in this list, but our subquery actually returns a table, not a single column. The in needs to have a single column table. So obviously we need to reduce that here to PID. So we only want to have that column where the person IDs for those person in that table with the role 4 are in. And then we can run that against here. And you see now we get our 2, 3, 4. And you see also, interestingly, the order of these records of course gets determined by the main query, unless we do a specific ordering. So the subquery just creates that list as a filter condition for your query. Right, so there you have your subqueries used to filter. Of course you can spin these ideas on in a whole range of different ways, but these 2 are really the most commonly one, the Scala subquery and the single column subquery that feeds into an end clause. By the way, when you look at this last example, you may rightly say, is that not something we could do with a join? And you're absolutely right, we could, but we're going to look at that comparison between subqueries and joins at a separate lesson. Let's take a look at the exists clause. The exists clause is particularly interesting and important with subqueries, as it gives you another twist on filtering your records based on a subquery. Also again, it constitutes a possible alternative to a join, and again the discussion about joins versus subqueries we're going to cover in a separate lesson. So as usual we're starting from our select star from person, and what we want to do now is we want to filter out again those persons that have any project assignments, which of course we see in that table. Now the difference to other subqueries is that your exist clause basically just checks whether your subquery returns anything or not, and based on that filters. So we're going to use our select star from person and then do a where, and the keyword here is exists, and then we get our subquery in. Right, and the subquery is our select star from the project person, which now needs a where clause. And to really make sense of a exist style subquery, you need to create what's also known as a linked subquery. Because again, you need to remember the set-based nature of SQL. Obviously the subquery is supposed to filter the records in our main query, so it needs to look out if basically on a per record basis the subquery satisfies something. So if you have a complete independent subquery, it will create some rather peculiar, likely unuseful outcome, in that it will just filter in or out all records, so it's kind of not doing anything. So what we're going to do here is because of that we're going to use our table aliases again, and we basically put in here what else we would have used as a join clause. So we have PID equal PPP ID. And so you see, and quite often you will actually find, though it does of course make no difference, that people put it the other way around to basically say, well, select star from project person PP, where PPID is, and then that is a referral to the main query. So if we do that, then we're going to see that we get 5 people. Remember, we have 6 people in our person table, but we have 1 person that obviously has no assignment, and of course we can do that the other way around now by doing a where not exists. And you see, then we get that 1 person, Sue Baker, who doesn't have a project assigned and therefore doesn't feature in that subquery. So what you see structurally happens is the where clause basically for each record in person will evaluate the subquery and thereby filter which persons are shown or not. And obviously you can drill that further now. We've before had that idea that we've said we're gonna filter on the role ID, so we can do that again and say PPRID was the field for that equals 4, for example. One further down. There. And you see now we get those people who are assigned on that role ID 4, which was our tester on this occasion. So that is your exist clause, and as said, it's a very handy one when you just want to check whether your subquery results in something or not. That's also why we can use the select star in here, and we don't need to worry about what exactly it outputs. Experience also shows, but if in doubt you want to test that, most database query optimizers nowadays are clever enough that it really doesn't make any performance difference whether you put a select star there or something more decisive. There's always rumors around performance optimization out there, and with a lot of them I tend to be careful, because it unfortunately too often is rumors that are not founded on actual facts. So here in the exist we therefore can just use the select star, because all the exists will check is, does the subquery return any result or does it not. Another interesting bit to mention here, of course, is because of that linked subquery, you can't test the subquery in its own right, which can be a bit a tricky one. So sometimes you need to find ways around that to see if you can test your subquery to make sure that it actually creates the right thing. So there you got your exist and not exist clause for the subqueries. Let's have a look now at subqueries versus joins, or as an alternative to joins, and the whole discussion about which one is better or not, as I've mentioned on a few other occasions elsewhere already. I've pulled together some of the queries we've used elsewhere here, and we're just going to see how they convert into each other and how they show alternative ways of achieving the same result by either using a join or some kind of subquery. So we're starting obviously off with the join here. So our usual implicit inner join that joins the person table, the project table, and that hands us out all those people with an involvement in any project with a particular role. Here's that role 4. And of course I haven't filtered anything further down, and you see when I execute that, you see the output here. So we get 3 records. Interesting maybe to note the slightly unexpected ordering of the person primary key. That's things that depend on your individual database system, how queries are optimized and so on. So if you're particularly concerned about this, you want to put in a decisive order by. If you don't worry, then well, so be it. So that of course is a reasonably straightforward inner join that achieves that list. Alternatively, of course, we've seen you can do that with a subquery that actually uses an in clause. And the list used in the in clause is created by the subquery. So our subquery here, if we execute that alone, creates us a list of PIDs for person in that table that have that role. So I can execute that in its own, of course, and you see there we have our PIDs, and then I can execute the whole thing, and you see we get the same result as in the others, pretty much the same result, except the order is slightly different, and in the first query of course we got all the additional fields from our other table, because obviously we've done a select star on 2 tables and not just on the person table. But the essential data that typically you will want to see are the same as you see. And the third version, of course, we could do this one by is using a subquery with an exist clause, as we've seen before. Such a linked subquery that basically maps the person and the project person in a way. And again, if I execute that, you see it creates the same kind of output. Now the question, of course, is there really any preference in each direction? And as far as I'm concerned, the clear answer has to be no. There is a lot of discussions going on about performance optimization, especially in that area. But you really want to double check that. Left alone that often enough these queries have runtimes which are really completely pointless to optimize. But if you're worried about this, you want to make proper tests, and you probably will find that depending on what kind of database system you use, the outcomes are different. All the big database products, the like of SQL Server, Oracle and so on, have very advanced query optimizers these days. So quite often you find that actually the outcome is exactly the same. In these more advanced systems you often find tools where you can actually trace how the database has evaluated any of these three queries, and sometimes you will find, oops, it's actually doing the same for all three of them, which just tells you how clever these query optimizers are. That of course is the selling point of a good database system, that it has very good strategies of executing a query that you write in the most efficient way. Quite often I find the distinction between these three versions, and I'm actually going to open that screen a bit further so we can see them all three at the same time. You will find that people have a preference for them simply by the fact what works best in their mindset. Some people quite like this kind of in style because just from the logic it's easier for them. Other people prefer the exist because it's easier mentally for them. And of course there's people who find subqueries in the first place a bit strange and complicated and prefer a straight join. None of them is wrong or right. In almost all cases I've looked at, there is no real difference between it, so you may just do it the one way or the other way. But be aware that you may come across that discussion whether the one or the other is better, and the clear advice has to be, if there is a concern about this, the only way to find out is test it against your database system, do performance measurements and decide on the numbers. There is no way to decide that in a theoretical discussion. So there you've seen on this occasion three different ways of doing the same query by using subqueries or a join, and you will find a lot of scenarios where you end with such kind of alternatives. In this lesson we want to learn about derived tables and their use in subqueries. So what's a derived table first of all? Obviously if you look again at our select star from person, the person is the real database table we're using here. There's all kinds of scenarios where it can make sense to create a kind of table on the fly, and that's what's called a derived table, because you're basically using a subquery that creates a tabular output and that becomes a temporary or a derived table. Again, that is quite handy when you need to do some pre-consolidation of data, for example. So what we want to do here is build such a derived table and use that step by step in a cascade of subqueries to eventually arrive at a query that outputs us the manager with the most direct reports, which of course if you look at that you can already tell is our CEO Rick Walker, who is a manager ID 5, to report 2. So we're starting with our derived table, which is nothing else but a SQL query that creates a tabular output. So we're going to do a select from something which we need to determine in a moment. Person. And we want to, because to find out who has the most direct reports, of course we first of all need to do a group by consolidation, and we group by manager ID. And then of course we want to output the manager ID here, and we want to output the count star for that manager. So that subquery is something we can test first of all. And now we see we have our managers with their number of direct reports. Now the next thing we do is we're going to stick that into a further query, which further consolidates these data. And now what we want to find out, we want to find that line with the highest number of direct reports. So we do a select max direct reports from, and you see now we have our subquery coming in here. And again, it's common practice to put some brackets around so you see what you're actually doing. So we're basically, we've consolidated once and then we do a consolidation on that, and you see that's where our table, our column alias here comes in to use by using that up there. Also, you always need a name for that table. So if you do these kind of derived tables, they always need to get a table alias, or basically a table name, so they can be referred to. So I'm just going to call that counts. So if we run that, you see then we get our 4. So that gives you an idea about the use of derived tables. There's all kind of ways you can use them. Of course you could use this select max we've just done now as a filter in a further query that sits in, whether it would be in the where clause, in a having clause, or something like that. So that way you can create these kind of subsets you work against. You want to be maybe careful in very large databases, because in the end these temporary tables need to be stored temporarily somewhere. There's situations where again the query optimizer will just optimize them away, but there's also situations where they can create quite sizable overhead. But as such they are an interesting feature to do a whole range of activities. Let's talk about the insert statement in this lesson. The insert statement is one of 3 statements belonging to the so-called data manipulation language part of SQL. That is the insert, the update, and the delete. So all 3 are statements that allow you to change data in the database. Not changing the structure, but changing the content. In all the other lessons, we've mostly looked at the select statement, which only allows you to read the data from the database, but you don't modify the data. So the insert now allows you to add new records to your database table. The insert might be slightly misleading in its wording, in that it not actually is an insert at a particular position. That's something the database takes care of in means of indexing and the likes. Quite often it will be just an insert to the end of the table. One thing which is important whenever you do inserts, the same as when you do updates, which we look at a separate lesson, is that your data need to satisfy all the rules in your database. And that's why I've pulled up that diagram here again. So let's have a quick look at that. First of all, when we look at the person table as an example, which we're going to use here, we have the primary key. One thing that's actually not visible on here is that these primary keys in that database are set to what's known as an auto increment in MySQL, or SQL Server and Access call it identity. Oracle has a similar strategy called sequence. All of them do basically take care of the primary keys themselves by assigning the next sensible or useful value. So you never will insert the primary key yourself, you leave that to the database. Then we have the first name and the last name, and if we sit on them, you see they have the not null flag, as you also can see with this solid diamond, which means out records, these fields are mandatory, we can't skip them, while the other ones are set to null as a option, so it means we can omit them. And finally we have that created timestamp, which is not null, but at the same time you see that it says default current timestamp. So again, that will automatically set the current timestamp in there if we don't put any other date in there. So these kind of null and not null rules we need to support. And if, for example, we were to insert records in another table, in one of these related tables that have key values that relate to other tables, then we need to make sure that we insert data in there that actually exist. So, for example, we can't assign a person that doesn't exist to a project. If we want to add somebody in here that's not generated as a person, that won't work. Equally, we can't assign a person to a project that doesn't exist. So in these kind of M2N tables in particular, but also in any kind of foreign key situation, you always need to make sure that the data you insert here are actually representing valid values in the referred tables. Good, let's see how we do this. We're going to use our person table again as a starting point. Good, and I'm going to do a first insert. There's a couple of subversions I'm going to show you here, and we start with the basics, of course. So the whole thing starts with insert into, and then we do the table name. By the way, you can in principle only insert into one table at a time. There's a few notions in some later versions in SQL to do inserts on multiple tables, but I'm rather wary about this. The traditional line is you may join together data in a select, but you always only do manipulation on one table at a time. And it just makes it safer and easier to keep your hands on, that you don't violate any of these constraints, of course. Right, so we have the insert into person here, and then we have a construct called values, which in round brackets gets in a comma separated list the values that you want to insert. Now what I've started here is what's known as an implicit insert. which means because we are not saying which columns we want to populate, we need to put them all in, and more importantly we need to put them in exactly this order, because the insert will match that automatically. The big pitfall in that, and that's why I generally discourage using this version, is that you need to be sure that you know the order of these columns. And especially if you write a script or you write a statement in your application and then the database structure changes, of course your statement will fail. And you get these situations where a database gets changed and you add a column to a table, and sometimes people have that slightly silly idea to add a column in between two existing columns. When I add a column to a database table later, it will always go at the end, just to be safe. But you get people adding them in the middle, and of course if you've then used such an implicit insert, suddenly your order of columns doesn't work anymore. So your statement will either fail, or you're unlucky that it actually succeeds because it somehow manages to mingle the data types in a right way. But of course you get a complete mess of data in your records, and you really don't want to do that. One other wee constraint to keep in mind for the insert, and the same goes for the update and the delete later, databases don't have an undo button. So once you've sent it into the database, it's in there. There is no way to say, oops, I got it wrong, let's undo that. So you really want to be careful how you approach that thing. I'm going to show you the implicit one anyway in completion here. And you see now we need, as I said, because it's implicit, we need to state every single one. So seeing the database table in front of you helps immensely there. So obviously we need to have a primary key, because in this implicit version that idea that you don't set the primary key doesn't necessarily apply. Then we need a first name, which goes in quote. Let's add me for a change. Then we need a date of birth. No, I'm not going to tell you mine. For example, like that. So again, remember you need to find the right date representation here, that it works. We want a manager ID. Well, as 5 is already popular, we're going to stick to that. We're going to put some notes in, and we need to put a date in, and there at least we can use the now function to do that. So, and there we have our implicit insert. Now if I run that, then you see it's done that. And if I read my table again, there we have our record 7. Also, what you've seen here as a difference to the select, the insert statement doesn't return anything. That's why the screen goes blank afterwards. Now, next I'm going to show you the explicit version, which is really what I highly recommend to use. And there you put, similar in round brackets, a list of the column names that you want to populate behind the table name. So, obviously that would be first name and last name, because these are the mandatory ones. And say on this occasion we want to add the date of birth, and by the way, just for the sake of showing it, you see the advantage is also in this implicit version now you can mix up the order of the fields. And all you need to make sure now in your values area is that you put the right values in. So as said, we are not mentioning the primary key because that gets set automatically. So, and then we move that around, and this time I'm going to make myself 10 years older, and you see all the rest goes. So we've mentioned 1, 2, 3, 4 fields appear, and we enter 1, 2, 3, 4 values. And the rest gets default populated, which the notes is a nullable field, and the created gets the current timestamp. So we're going to run that again. So, and you see down here it says query completed. That tells you that it's actually gone through. And then we can do our select again. And you see now we have next one. And you see obviously at some point there's been inserts going on in the database already, so it hasn't used the 8 because the 8 was obviously used at some point in this database already, probably when I played around with it. So that's one of the interesting side effect of this auto increment and identity sequence style thingies. They take care of not reusing IDs, which is a good idea for security, to make sure that you don't reuse a primary key, because you may just suddenly link data in a relationship together that don't work. In particular, not all databases enforce your relationships. More and more database products have this so-called referential integrity, where they enforce your foreign and primary keys technically, but even MySQL still has a mode where it doesn't do that. So you don't want to reuse primary keys just in case you suddenly link data to each other that have nothing to do with each other. And you see that created date has been set here again. So that is our insert in some way. And now I can go by and say quite often obviously I want to do multiple inserts. And the traditional way is to simply run these queries again and again. And now if you want to do this as a kind of script, we need to do something which so far I've stoically ignored, is we need to finalize our individual statements with a semicolon. Only then we can run them as a block. So, and now I'm going to put somebody else in here and say, well, he's a little bit older. Let's make him really old. The database should be able to do with that, hopefully. If not, we'll find out in a moment. Right. So now we can run these two, and actually I should modify mine again by, for example, sticking yet another date of birth in, just so we can distinct the records. Of course, there's nothing wrong with having duplicate records, but just so we can distinct a bit better the records where which one comes from. Okay, and I'm gonna run that. And you see it's done that. So you see also here, that's why I always keep my select star on hand, because I always like to check on my data. I don't trust myself, I don't trust any statement. I always make sure I double check my records. So you see, and now we've inserted 2 more records here. Now the next version to that ability to insert multiple records is something that has popped up more recently in virtually all SQL databases and has become part of the standard, that you can actually do these multiple inserts in one insert statement. And what we do is we're going to take that part out and we take the values out. And now what you actually do, oops, that was one too much, you actually comma separate that list. Okay. There. Make it a bit look nice, and then we can do the same again. And you see now we have number 12 and 13 in here. So you see, all you do is, instead of having one set of values, you add a comma and put the next set. And again, as long as it's an individual statement, of course the semicolon at the end is not required. By the way, you want to be careful. Some databases want a semicolon always. For example, in Oracle, certain query tools always want a semicolon at the end of the statement. But that's one of the proprietary features. Okay, so there we have our multiple inserts. And the next thing we want to do is that, of course, you can also do an insert by selecting from another table or from the same table, so you can copy data basically. Where this version with the values is quite handy for populating a database. I always run backup scripts of my databases, and if I, for example, need to install a database on a production system after I've done it on my production and my test environment, then I just take the export script and re-import this on production, and that way I can populate all my data. And then you find these long lists of inserts with values in there. But equally you find situations, for example in data migration, where you actually want to copy data within a database or between different databases, within one table, between different tables. I'm going to show you how that works. And the thing is reasonably straightforward. Basically we create a select statement, and of course we're going to test that alone first again. So we obviously need a select statement that returns us exactly the structure here. So we may just as well copy that from. And on this occasion we're just going to copy within the table. So from person, and then we give it a where clause and say, for example, where ID larger equal 10. So we want to copy the last 4 records we got there. And now, for example, we could do a wee tweak on it and say, just so we can identify them, we actually gonna use our concat function to say copy of. So instead of just sticking in the first name again and again, we're going to stick in the first name prefixed with the word copy of. So now if we just mark that part, of course we can run our select again. And again, like in so many other areas, the suggestion, always do that first, so you know your select is doing what you want. More so in these kind of data manipulation activities, because the last thing really you want is to select copy data into a table and afterwards say, oops, that was the wrong ones. Especially if you've done that with more than 3-4 records that you potentially can clean out manually. If you've done that with some bulk data insert, well, there's no way you can clean that up. So you want to be, again, better safe than sorry. So I'm just going to run that select statement to see that it creates us what we want. And there we go. There we have that. So now I can run that insert statement. So you see, all you do here is you glue that select statement right after the insert into statement. You lose the values because you're not doing values, you insert data now, and then you can run that. So, and if we take our select star again, then you see now we have these 4 records there. So that way you can very nicely copy data in a database. And of course you can do this with every possible concatenation we had so far, in means of complicated where clauses, in means of course having a select that is actually a join. Yeah? For the select part you're perfectly fine to say, I'm going to populate the content of a table with the result of a join from multiple tables. In the end, that's exactly what you do in database warehousing, where you create data warehouses by consolidating data in a production database. So there you have a another field of lots and lots of variation you can play with, and you can create whatever suits your purpose. Well, and that's the insert statement for us. In this lesson we want to talk about the update statement. The update statement is the second out of the three data manipulation language statements, which are insert, update and delete. So the update allows you to modify existing records in a table. Crucial to remember here is that because we're talking of SQL as a set-based language, your update will work on a set of records and not on one record only, depending on how you run your update. And we see that in a couple of examples in a moment. The other thing to remember, of course, is the constraints. As we've said in our person table, which again will be our guinea pig here, we have certain fields that are mandatory, which can't be null. There are certain fields who can be null, and also, of course, if we go on into other tables, we would have fields where there are relational constraints. So you can't run an update, for example, on these M&N tables that violate their rules there. So you can't update the PID in the project person, for example, to a person that doesn't exist. And finally, of course, the warning again, there is no undo. So you really want to be careful when you do these updates, because once it's done, and getting it corrected when you got it wrong is an awfully complicated task. Right, so how do we do our updates? The statement here is, and you see I'm using my select star from person again to see my table, the repeatedly made recommendation already, have your table on hand so you see what you're up to. So the update statement now is called update, as you would expect. Then it gets the table name, which is person. Then it has a set clause where you say what you want to set. And for example, I could say I want to set the date of birth to something. 1990-01, for example. Now, if you were to run this statement as it sits there now, you would have some rather certainly unwanted tremendous effect, because this would update every single person in your table to this date of birth. And I'm pretty sure that's not what you want. So the bottom line to remember with these DML statements, like update and delete in particular, is really that kind of credo of SQL I've mentioned elsewhere. The shorter your statement, the more damage you do. The more records you affect. So here, because we haven't specified which records we want to update, it will update every single record in your table. So I'm not going to run this query because it will completely screw up our database table, and we don't want that. What we instead need to do is we need to add a where clause. And that where clause goes exactly the same lines as the where clauses we've been discussing in the various concoctions of SQL statements, of select statements. And that is why you spend that much time on learning and explaining select as a statement, because all the various bits and bobs of where clauses, of subqueries, of joins and the like you've learned there all apply to the update and the delete statement as well. Which in turn means the safe way to do that is to create your where statement first of all as a select. So you actually see which records get selected and you say, yep, that's the one I want to change, and then you go ahead. So we're going to do that. Now, of course, the easiest, as we've had, if you want to be sure that you change just one record, you're going to use the primary key, so the ID in our case. And you see down here we have a whole range of rather chaotic records, which are obviously leftovers from our insert lesson. Which is fine, because that is data that doesn't really do anything else in the system, so we can play around with them and mess around with them as much as we want without doing any damage. So I'm going to use the ID 10 here. Now, if I execute that, then of course, as I expect, I get that one record. So now I'm gonna copy that one down here. We're gonna look at that record before we execute it. So we want to change the date of birth to the 1st of January 1990. So that's what we want to see afterwards here. So we run that one. And similar like with the insert, it only shows us a query completed, nothing else. It doesn't show us any results. In some query tools you will see that it shows something like so many rows affected. So on this occasion it would say 1 row affected. Now I'm going back on my select star, and there you see now we've changed the date of birth in there. Everything else is as was. Now I can drill that on and can change multiple things in a record, of course. I don't need multiple update statements. I can do the set strategy as a comma separated list. So I could, for example, say I'm just gonna change the first name to Mike. And obviously, because we've tested the where clause, now we can use that. So, and then we can execute that. And you see, query completed. And if we're going to go back, now I've changed my name to Mike Holzke. And you see also, of course, as you would expect, it doesn't matter that actually the date of birth had already the right value. It will just say, well, I changed it to the value you asked before. Next, of course, we want to change more than one record, because there's of course a lot of scenarios where you deliberately want to change a whole set of records. So I could, for example, say I want to change all the other records where I'm still called Martin to Mike as well. Which means obviously I need a where clause looking on Martin. Now if I do that, then I see there's 3 other records that are still set to my real first name. So obviously now I don't want to change the date of birth. I'm not bothered about that, but I want to change the name. So I copy my where clause down here again and execute that. There we go. And now if I go back, first of all, if I use the full filter, I see that doesn't return anything anymore because all these are changed now. And now if I go back, of course I see that all of them are changed. And of course now, to bring things back in order, of course I can change that back, because you see now I have 4 records here that do that, and I'm going to change them back to my normal name. And there we go, there we are all changed back. So that of course I can do in all kind of different shapes and forms using whatever criteria. Of course, I could just as well now go by and say I want to change based on another criteria, like on the last name or the date of birth. I want to do some changes. So obviously the where clause and the set part are not interlinked with each other. You can pick and mix that as you like. And equally you can use all these kind of functions that we've looked at elsewhere in there. So you could create any calculated values. And that's something I want to show you on a separate example now. One table where we can do a bit more numerical stuff, which we can't really do in the person table because there's nothing suitable, is the project table where we have a budget. There I want to show you a scenario where indeed a handling on the whole table might be desired. So I'm going to clean out here quickly a bit, and we're going to look at the project table now. So you see in that project table we have 3 records at the moment of different projects, each with a record. And of course now it could be that I say I want to upgrade them all and I want to increase the budget by say 20%. So update project set budget equals budget times 1.2. So that would of course now increase all of my records in that table by 20%, and that may well be an operation I want to do. So memorize the numbers quickly here, 2000, just under 1000, and 250. And now if I run that and then go back to that, you see now our values have increased. And of course now I could reverse that activity and there we go, we have our data back. So you can do these kind of mathematical operations in there as well. And that's just one example out of many what you can do in intelligent activities in such update statements. Of course you can use subqueries again to either get the value you're setting or to use as a filter, as a where clause in there, and so on and so on. So that is our update statement. So really the crucial bit to remember, unless you have a really good reason, never ever forget the where clause, because the where clause is really crucial, else you're updating your whole table. And in my experience, in 99.99%, this is not what you want. Let's take a look at the delete statement now, which is after insert and update, the third of the 3 data manipulation language statements of SQL. So what we are looking here is the ability to delete one or more records in full, like for example this line, or 2 or 3 of them. We are not talking about deleting individual column content, because you can't do that. If you want to do that, you need to use your update statement to change content of individual columns. So a delete is a delete of a full record or multiple full records. For the delete goes exactly the same what we've already said in the context of insert and update. First of all, there is no undo in a database, so once you delete a series of records, they are gone and there's no way of getting them back. Equally, when you delete records or when you attempt to delete records, you need to make sure that you don't violate any of the constraints in your database, be it constraints on the table or be it constraints by relationships. So for example, you can't delete a person from this table that is still used in any of the other tables, for example, is assigned to a project. So, how do we do that delete? The base statement is simply delete from, and then we have the table name. And again, as before, the simpler your statement, the more damage you do. So if you're going to execute that, that will completely empty your person table, which quite likely is not what you intend. So always remember you need a where clause. And in a delete scenario that is even more so true. There's very few occasions where you really want to empty a table altogether. So, and again, the easiest is of course to use a where clause that just affects one record. And again, similar like I've discussed in the update, always make sure you test your where clause beforehand, just to be sure that you have the right amount of data on your hands before you delete them, because once you've in the delete found out that you deleted the wrong one, it's unfortunately too late. So what I want to do is I want to get rid of this one record here. So if I run that select, you see I get exactly this one record, which means now I can safely run my delete. And again, it just shows us the query completed here. And if I run that query again, of course it doesn't give us anything anymore because we've just deleted that record. But if we look into select, we see everything else is there except for the one with the primary key 10. So that is of course the most bulletproof way to get rid of one individual record, which is a pretty common scenario that you want to get rid of a particular specific record. But of course also you have situations where you want to get rid of a whole block. For example, I could say I want to get rid of all these copies I've done down here. So again, I'm going to create my where clause for that. And of course I could just go by and say, well, let's use the ID or whatsoever. But of course often enough you use other criteria. So here what I'm going to do is I'm going to check on the first name and use the like statement we've seen at some point and say I want everything that starts on copy and continues with whatever. So again we run that select statement and we see, yeah, there we have those records we want rid of. And then I take that where clause and stick it in here and execute it. As said, elsewhere some query tools give you an output saying so many rows affected. MySQL doesn't do that by default, so there's ways to get that if you need it. Right, and then I do my select from person again, and you see now all these records that were here at the bottom are gone. So that is your delete statement in various forms. And of course again you can now go by and use all kind of tricks that we've learned before in your where clause to build all kind of conditions for your delete. So all the complex where clauses we've looked elsewhere, all your subqueries, your joins and so on, all of that you can use to control what records you delete. Remember though that by default the rule still stands that a delete is always on one table. I've mentioned elsewhere there is a drive to loosen that rule, that you can do deletes on join tables, but I'm certainly not in favor of that. It is much safer and much easier to control, to keep your deletes to one table at a time. So that's us complete with the delete then as well. In this lesson we want to talk about transactions in general. So we're not going to have any example, but I'm going to show you a bit around what transactions are all around. And in the following lessons we're actually going to use the individual features. So here we want to first of all understand what transactions are all about. In all the other lessons so far we've looked at individual SQL statements you would execute, selects, inserts, updates, deletes, and so on. There's a lot of situations, of course, where you would execute groups of statements that you want to either all succeed or none. The traditional example, of course, is a bank transfer. You take money out of one account and transfer it into another account. So that may be two individual update statements. And of course you want to make sure that all that only works if both statements succeeds. If the money comes out of your account and doesn't reach the other account, then the bank has won, and none of us really would appreciate that. So the transaction allows you to build a bracket around multiple statements, and it really only is interesting for insert, updates and deletes, where basically all these statements are executed, and at any stage within the transaction while they are executed in a temporary matter, and only when the transaction altogether succeeds or is committed as it's called, then all these changes that you've done within the transaction are actually properly written back into the database and fixed. If something goes wrong, you can roll back the transaction at any point, and all the temporary changes, intermittent changes you've done to that stage in the transaction are rolled back, are basically forgotten. And that's really what you want to have as a security feature when you do complex operations, because else, of course, you would do some changes and fail other changes, and you would bring your database, of course, in an inconsistent state. So that's certainly not desirable. At the same time, with these transactions come so-called isolation levels. And these vary slightly from database to database, but the base idea is the same throughout, that while I do such a series of operations within a transaction, I want to control what other users of the database can see or can't see. The typical one is, of course, that as long as I am in the process of doing something and I haven't committed my transaction, other users won't see these changes. So if I take an awful long time, then I may change some data on the database, but the other users still see the old stage because I haven't committed my transaction. Equally, that means that during that time other users can't change these data that I am just changing, because else we would of course override each other's activities. For that reason, you always want to make sure that your transactions are short and sweet, because else you just log each other. In particular, as some databases have very interesting ways of handling transactions, even if you're only changing a single record in a table. In some databases that may cause a whole block of records being locked, which is then known as a page lock typically, or in some operations the whole table gets locked, which means nobody else can change on that block of records or on that table. Sometimes actually other people can't even read that table anymore. So if they run a query against that table, then their query gets stuck until your transaction commits or rolls back. So it's important to keep these things in a good short way. So you shouldn't have open transactions in an application that allow for the user doing something, then deciding to go on their lunch break, and the transaction is still sitting there. Many databases sort this through timeouts on transactions, that if a transaction exceeds a certain length, it just simply gets automatically rolled back. So that's the kind of idea about transactions, and as said, there is different ways of handling it in detail, which is a major subject in its own right. We want to leave it here at the basic understanding. In this lesson I'm going to show you how to initiate a transaction and also how to see the effect of such a transaction and the statements executed in the transaction. To be able to see this, we need to have two different user sections, so we can see that idea of isolation between the transactions. So what I've done here, I've opened two instances of my SQL editor. It's important that it's two instances of the editor and not just two query windows, because at least in this tool the query windows don't act as individual sessions. In some database systems and some database tools it does, so you want to look out if you use whatever you use. And you see I'm just using my normal select from person query to see my person table. So I have it once here and I have another one open here which shows me the same kind of data. Now I'm going to start a transaction on this one and gonna do some changes. So, and the command we want here is start transaction. And because you tend to execute that as kind of batches, it's important that you terminate the statements with semicolons. Right, and what I'm going to do is I'm going to do an update on this table. You see Susan Baker here is the one who doesn't have a birthday, so I'm going to update that record. And what we're going to see is that once I do this, as long as I have this transaction only started and haven't done anything with it, like committing it or rolling it back or the likes, I won't see it in the other session. So we want to update person. We want to set the date of birth. Oops, that was a 0. Date of birth to some date. For example, like that. And we want to do that for ID 6. So for that record. Now if I execute these few lines, of course I don't see any result because that is just an update. And now if I run my select again, you see the record here has been updated. Now if I go over into my other instance and run my query there, you see there it still sits on null. So I see here that I have two isolated versions going, because I'm in a transaction. I've started the transaction, but I've not finished the transaction in any way. And the different options of finishing the transaction, in means of committing, rollback and so on, we're going to see in a separate lesson. So there you have your start transaction command, and by the way, you find that in different database systems they are slightly different. Sometimes they're called start transaction, sometimes they're called begin transaction, sometimes they were called begin trans and so on. Unfortunately that's one of the areas that are slightly less well standardized. Right, so that's our transaction initiate it. In this lesson I'm going to show you how to complete a transaction. We're going to continue on from the example we've started in our lesson about initiating a transaction, which you can see here. So we've started a transaction, we've done an update to that record here, and we can see the change being made there, where in the second session, which we've opened, you see it still sits on 0, because obviously as long as we haven't completed our transaction, we see only the changes in our own session, and other users don't see the changes. So now that we are at that stage, I have two options. I can either commit that transaction to actually fix this change in the database, or I can roll it back. And because it's easier in means of demonstrating it, I'm going to start with the rollback. So if I decide actually, no, I don't want that, something been wrong, I want to roll back this transaction, then I can simply issue a rollback here. And it says completed. And now when I look on my table again, I see my changed data here is gone. And of course, just as proof of the pudding, of course it's not here either. Right, let's do the whole thing again. We start our transaction again to that stage. And we have a look. Yeah, there's our date changed again. And here we still see no date. Right, so this time we are gonna commit our transaction. So once I do that, then yeah, my data are here. And if I look into the other session, there's my data there as well. So the commit has written back the changes permanently into the database, and that's my transaction completed. So what you see quite nicely here is you can play around with these transactions if you want to try out the mechanics by just running these statements step by step and use multiple sessions to see what's happening. And that's a good way to get a feel for these transactions, because it's not necessarily something that immediately springs to mind how that works, and thinking in this kind of multidimensional way to say, well, what I see others don't necessarily see. Also, it's if you have these environments, a common pitfall, of course, when you change data in a table and then pass it on to colleagues and say, yep, it's done, and they look and say, no, it's not done, it's still the old, and say, no, but I've done it. And often it's the lack of a commit. In particular, in some database systems, Oracle has a reputation for that, for example, you traditionally not necessarily have an automatic commit. So even if you haven't specifically started your transaction and you do an update, you may have to specifically put a commit after that, else it doesn't end properly in the database. So you may want to watch out for that, because it's a beloved field of confusion. I've fallen into that trap many a time, that I've changed something and proud say to everyone, yeah, it's all changed, it's all updated, you can use it now, and minutes later they come back, we can't see the data, where are they? Oops, forgot the commit again, bugger. So that is your committing and rollbacking of transactions. Probably the most important statement within SQL to create database objects is the create table statement, By the way, all these statements are summarized in what's known as a data description language, or DDL. So here we see our database diagram as usual, and of course each of these tables we have in there needs to be created first before we can put data in there. So we want to see how you create these tables, and we're going to replicate a few of the tables we already have in here by our own create table statement. So I'm starting with the person table, which we've used so often, and here you see the create table statement for that. So the whole thing starts on this line called create table, then the table gets a name, and because it's a replica of the person table, I just simply gonna call it my person, or whatever else you fancy. Then you see it has a pair of round brackets and a semicolon at the end. And that is basically your body of your create table statement. And then you have in the middle a whole set of lines which specify the table. So we have first of all a line for each column in this table. So we have our ID, our primary key, we have a first name, we have a last name, we have the date of birth, the manager ID, the notes, and our created date. Exactly what you see here in that part of the diagram. And also then we have next to each of the column names a data type. For example, the ID is an integer, so a straight number, and the 11 means it can be up to 11 digits large, which is just a simple 32-bit integer, which you use on most database systems these days. And that is perfectly enough. That is a number well beyond what you normally ever will experience in unique IDs in a database, unless you go for something really wacky, geospatial or something like that, where you need a hell lot more data. But for everything normal, the int 11 is perfectly fine. Then we have our first name and the last name, and both of that of course are textual values. So we're going to use for that the varchar data type, and the 255 is the traditional default for that, so it's 255 characters. Now you may say, why would you put a first name on 255 characters? Well, first of all, it's very difficult to work out what the best length would be. If you go through different parts of the world, you will be surprised what kind of long first names, or worse so last names, you get when you get in parts of Europe, all the kind of royal names, all the kind of earls and dukes of whatever, or you get in some parts combined names where when people marry, one partner keeps their maiden name and appends their new family name and all kind of things. So it very quickly goes quite lengthy. So I just always put them on 255 because that is the old standard. Most databases meanwhile actually allow more than 255 in varchars, but the 255 normally does quite well. And the trick with the varchar as a data type is that that's where the name comes from. It stands for variable character. It means it adjusts in length automatically when it stores in the database. So in the end, you're not actually using up 255 characters no matter what. The database actually only uses up as many characters as you put into the field, plus one to keep the length. So in that sense it's quite an efficient and at the same time safe way of saving your data. You may have seen yourself systems, websites or so, where suddenly you have a limit on what you can put in and you say, but I want more, I need more, some of my details don't fit in there. So that's the best way to cut out that problem. Good, then we have for the date of birth obviously the date data types, and we have that manager ID, the reference to the manager of that person, which again, same as the primary key, is the same type. Then we have that notes field, which has a data type text, and text is the extension of the varchar. Text is a much larger text blob, and depending on database, that can take tremendous amounts. On some databases it can take something like 4 GB meanwhile, so you can get a medium-sized book in there very easily. And again, it is of course flexible variable in the storage model. So if you have huge amounts of text or potentially huge amounts of text, I would always use the text data type. So for things like notes on such a record, for comments and the likes, I always use notes, always use text, because that way I'm sure I don't run out of space. Right, and finally we have our created, and that was that timestamp we've been using in the database, and therefore it gets the type timestamp. And finally we have one special line here, which is the primary key. So on the one hand there is ways, and some databases support as well, some not so, that you can actually specify the primary key in the line where you define it. The alternative version is to stick it at the end and just use that keyword primary key and the ID or the field name, which is here the ID, in round brackets behind it. It also means it makes it easier if you have a composite primary key. A composite primary key you can only declare that way. So this kind of primary key that we've seen in some tables, if I jump over here, for example, on the contact table, where the combination of PID and CTID is our primary key. You couldn't do that inline. So that's our generic create table statement. There's quite a few platform-specific options coming with it, and I'm showing you some of them in a moment. One particular area you want to look out for is the data types. Different database systems support different data types, different flavors of data types, and that is particularly true for dates and times and timestamps and the like. But on the whole, that works quite well. So before I show you these specifics, let's execute this bit here and see what we get there. And you see it goes pretty quick, and it just says query completed down here, because obviously there's nothing to output. This only creates our table structure, and as we can see when we do a normal select on that, there is of course no data in there. So we see we get an empty table. Another interesting feature, again slightly platform specific, is the describe function, where you can actually get information about that table. And you see there it shows us our database design just in the way we've just set that up. As said, that is somewhat platform specific, that it's not really in the standard, but more and more databases support that in the one or other way. Some databases call that show, others call it describe, so you just need to look out in the documentation which one is the right one. Good, so let's have a look at some specific code. So here I've prepared the MySQL specific create table statement, and actually I haven't created that, but that's taken from the database export of our database, which you have in the files coming with it. And you can create these backups typically quite easy through some functionality. PHP-MyAdmin has an export functionality, and you see then it comes out in this flavor. So there's a few differences, like for example MySQL always quotes all your table names and column names and so on, but that doesn't really matter. One particular interesting one is this auto increment statement here. That is this idea that you find in many databases, that the primary key is populated automatically with always the next value, and of course we've kind of used this on various occasions, and I quite like that feature because it gets you away from having to worry about primary keys. as they never have any business purpose, it doesn't matter what number you have unless it is a unique number. So in MySQL that's called auto increment, and coming with it is this thing in the bottom, which basically records when you export your table the last value used in this auto increment. Again, different database systems slightly differ here. For example, SQL Server calls that same thing identity. In Oracle it's called sequence, and it's a completely different concept and different setup there, but the idea exists throughout many systems. And then you see we have a few MySQL specific things here. MySQL has different kind of database engines that you can use, and it defines something like a default character set, so what kind of international character set you have, and because it's a European product originally, it goes for this Latin one set, but again not really particular crucial. And finally we have in here this if not exists, which is quite a nice statement because it means the create table statement only runs if that table isn't already there. Normally with all these create statements, if you try to create something that already exists, then it will cause an error. So with this if not exists statement you cut out that problem. And again, various databases support this in various flavors. Good, and finally in the next example we want to see some additional bits and bobs here. And that is in particular our foreign keys. If you remember, we also had our contact table, if I go on our diagram, down here. And of course that contact table had foreign keys to these two tables. Now, how do you set them up? First of all, you see it looks the same as before, but now we have that key column, which basically identifies that contact type ID as a key. And the way these MySQL scripts do it, they actually use a statement called alter table to add a constraint, because these foreign keys, of course, as we've discussed elsewhere, are constraints. And one of the common way in many database scripting languages is to first create the table and then with alter table add these constraints. You can build your constraints into your create table, but the pitfall with that is that of course you need to then create the tables in the right order, because obviously you can only set up a constraint to a table that is already existing, and that can be a bit tricky. So this alter table version has its advantages here. And you see it simply does an add constraint. Each constraint gets a name, and automatically you see they are a bit kind of cryptic, but that way they are unique because the constraint name needs to be unique. And then it basically uses that foreign key and that references keyword to basically link these foreign keys together. On the side we see here therefore this alter table statement that can also be used to change the table structure, but I generally avoid that because it's rather tedious to change a table once it's created. So especially as long as you're developing a system, it's much easier to just destroy the tables and recreate them than trying to change them with an alter table. If it happens to be that you have a system which is in production and which is complex and large, then sometimes you have no alternative, but that is a job I quite happily leave to people who enjoy this kind of work. Good, and that also leads us to a last statement we want to see here. And I'm going to go back to our first script and do that there, so we have that all together there. And that is of course the ability to get rid of a table. So, and that is the drop table, and then the name. And now if I execute that, then you see again it goes very quick, and then my table is gone, as I can show, for example, by trying to do a select on that table or trying to do a describe on that table, and it will not go anywhere. Worst case here in this tool, it tends to hang the query, as you can see, executing, 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 and still executing. And if I try the describe, it still doesn't go anywhere. However, if I recreated the table now, because it's gone, I should be able to do that. You see, there we go, it's gone. And now I can do my select again, and I got a table again. And I can do my describe again, and then I can drop it again. So that's kind of the trouble you find in all these data description language statements. You always get a create, you get an alter, and you get a drop. So you create it, you can change it, and you can get rid of it. And that is really what we need for our create table here. In this lesson we want to have a look at what views are and how we're using them. So, of course, the first question is, what is a view? A view is basically a prepared query that you store in the database, which then whenever you want to execute it, you can run it, and it returns you the data in that kind of prearranged way as you've put it into the view definition. So that is in particular helpful for quite complex joins and the likes. So we're going to look at an example here, and it all starts always from the query. So you create your query just as you would do it in the ad hoc way, as we've done it in all the other lessons here. So I've picked up an example here that we've used earlier, which basically pulls us together the various data pretty much through all our tables to show us which people are on what projects and what kind of contact details we have for them, as you can see in the output down here. Now, why would you want to use that as a view? Well, first of all, there's a likelihood that you need this kind of structure repeatedly, for example in a web application where you want to visualize these data in some way in a table or whatsoever. And one of the big advantages of a view, of course, is that you only need to develop that query once, and then you store that in the database and you have it, so you don't need to think about every time again how to get to that query. As you can see in that example, it is quite a bit of work. The second, probably even more important reason to use a view is the fact that when you actually create it as a view in the database already analyzes your SQL statement to work out the best possible execution plan for that. So in that sense, a view is performance-wise much better than an ad hoc join query. If you do that as an ad hoc join query, so you put that kind of query as it sits here into your PHP, .NET, Java, whatever code, then every single time you run that query, the database needs to sit down again and think, how am I going to execute that best? Where if you use it as a view and just execute the view from your application, the database has done that legwork already. So views are one of the big performance optimization features, where with very little work you can gain a lot of advantage. So let's see how we create such a view. As said, first of all you need to create your select statement as usual. over as many tables as you want or only one table, and you can do pretty much everything that we've seen so far in select statements. There's a few constraints. The one is you can't have an order by in a view definition, because else you would have multiple order bys, because you're going to use the view afterwards as if it would be a table in other select statements. And the other constraint for exactly the same reason is each column needs to have a unique name, so it can look like a table to the outside. You see this quite nicely on this output, that on first glance looks like as if you've just queried a table. So in particular in our example, because we have a couple of labels in here, because that's how our database is structured, so we have the pr.label, we have the ct.label, and so for that reason we need to give these columns proper unique name, as I've done here. And also, of course, quite obviously, if you had a column here where it said label or even pr.label or ct.label, that wasn't very user-friendly. And you see, for the same reason I've given that C value a proper name. So the goal is to have all column names in a proper expressive way. Good, and once I've done that query, all I need to do is now to wrap that into a create view statement. So I'm gonna add a line here in front, and that's exactly how you typically develop them. You build your query and test that, and then you do your create view. As every database object, it gets a name, and for example I'm going to call that project teams, because we see all project teams. And then there is that v keyword as, which is in some database systems mandatory and some not, so I'm just used to using it all the time. Right, so now I can execute that thing. Another reason why you want to get your query right up front is that, of course, every time you change your query, you need to recreate your view. So just playing around with a select statement until it is all round what you want is very easy, but this constantly creating a view and dropping it again, or altering and creating it again, is much more time consuming. So that's our view created, and now we can use it just as if it was a normal table. So select star from project teams, the name of the view, and you see there we get our data now. So, and of course it's obviously that kind of code is so much easier than having to do the whole complex select statement. So it's, as said, a huge level of performance but also convenience to use views, because it also means somebody can specialize in defining and creating these views, and then everybody else can just use them without having to think too much about the details. So it's a kind of specialization feature as well. Good, and of course, just as with every other data description language feature, if I was going to try to do that again, then you see it will get stuck executing query on and on and on, because the object is already there. So before I can recreate a view, I need to drop it. Which of course now means that query won't work, so that gets stuck. And once I recreate the view, I can use it again. And then of course I can drop it again to clean up my system. There's also a alter view, but I would just simply forget about it. If you need to change a view, the easiest is to drop it and just recreate it. So that's your views for you. So that's a feature you really want to look out for, because for all these kind of regular repetitive reads from a database, that is a highly efficient way. And I find this quite often on performance discussions that people tell me a database system is rather slow, and my first question is, are you using views? And quite often the answer is, what is a view? Okay, so obviously not using views. So if you have a database system which seems to be rather slow, it's the first thing to look out. If there's no views in there, then it's time to create suitable views and replace the code in the application with those view calls. It's much more efficient. And that's us done with the views. In this lesson we want to have a look at stored procedures. Stored procedures no doubt are one of the advanced features in SQL, and we're only going to touch on that here. There is plenty material in that subject alone to fill a course in its own right. But we want to see a few basics to give you an idea what you can actually do with stored procedures. Again, similar like with views, the idea is to bury functionality into the database, store it into the database, and that way have a pre-processed, pre-optimized query that can be executed whenever useful in your application through scripts and the likes. So I'm going to use this join query we've used elsewhere again, which creates us, as you can see in the output below, the list of projects with people assigned to the projects with contact details of these people. Now if you do it in a ad hoc join or in a view, you are naturally limited with what you can do, because you can't really parameterize this query. You can of course add a further where clause and filter on something, but that's probably as far as it goes. In a stored procedure you could do much more complex activities, and you could call it like a function in a procedural language like PHP and the like, so in a way that might be much more familiar if you're used to working in such languages. So how does that look? If I transform this join into a stored procedure, that is about what we get out of it. Now there's a few remarks to be made to that. First of all, this interesting delimiter and end of delimiter thing is a extremely MySQL specific thing. And I can tell you as a wee anecdote, when I did my first stored procedures on MySQL, I was humming and hawing because I did them as I was used to it from other databases, and it just wouldn't work. Until eventually I found somewhere in the documentation this remark that in MySQL, for whatever funny reason, you need to put these delimiter thing around. The formal argument is something along the lines that that redefines the semicolon that you use in your statement as no longer the delimiter of individual SQL statements, and instead you use something else, like for example the add, which you don't use anywhere else. As said, it's a really strange way. In other database systems you would just write your stored procedure like that, and that was you done. So in MySQL, remember to put this funny bracket around it. Now let's look at the stored procedure itself. First of all, again, because it's a database object, which is part of the DDL, database description language, of course you have a create. Only this time it's a create procedure. Then the create procedure again takes a name. On this occasion I've called this procedure project team, because what I want to do is I want to filter that join query we just looked at on one particular project. And of course you rightly say I could do that with a where clause. But it's just to demonstrate what you can do with these parameters. And you see in a moment when I use that stored procedure that it is a very different way of using it. Right, and then you have this begin and end block, which this tool nicely has marked with this kind of bracket. And that is the body of your stored procedure. So unlike the view or things like that, this one needs a begin and end and not an as. Right, and then in between you have your ordinary SQL code as we already know it, with one distinction, which is this one. If you look over on our base query, you see there PR label didn't actually exist because I put that as an extra filter here, and this one then links to the parameter I'm passing in here. So that is the other thing that create procedure command has. It has a round bracket and then it has a list of parameters, a parameter name and a data type, and you can have that as a comma separated list with multiple parameters. And then these values get stuck in there and are executing the query at runtime with whatever parameter you stick in there. So that is the way how to write such a stored procedure. Now the stored procedures of course can do much more. You can of course do inserts, updates, deletes in there. You can have all kind of complex conditional code, if-else structure, loops and the likes. I've recently done something with a stored procedure to create a complex cross-table, pivot table style thing. So it's a very powerful feature, and you can do lots and lots of things, but as said, it's way beyond the scope of this course. So I'm gonna execute that script and then our stored procedure will be in place. So as usual, I just execute that script, and again you see it completes very quickly. If it doesn't, then you probably already have the stored procedure in place and you need to drop it first again. Right, so and now I want to use that, and unlike all the other bits we've seen in SQL, the stored procedure is not executed through a SQL statement like select, but it has a special SQL statement which is called call. And then you give the name of your stored procedure, and then you need to have your parameters, and of course there you need to put in a valid name. So I'm going to pick on, for example, I'm going to use the project name website here. So as that is a text that goes in single quotes. Right, and now if I execute this, then you see there is our list of outputs. You see, by the way, what I didn't specifically say, I've reduced my select line here a bit. So obviously because I filter on the project team, it would be kind of silly on the project, it would be kind of silly to output the project here. Right, and now I can do that in a different way. For example, I could say I just leave that empty, and then you see actually this is a situation, because I haven't handled that yet, the stored procedure doesn't really like, because that won't work, which is a bit sad, because it would actually be quite nice if it just said, well, okay, if there is nothing with an empty label, then there is nothing. So we're going to pick something else, like we have here our Facebook app, for example, and we have, let's see what else we have in here. That's about it. So let's try that. So Facebook app, and then you see it works. So this kind of situation that actually your parameter is empty, there is of course ways you can handle that in stored procedures. So that gives you a bit the idea, and of course then we have finally again our drop procedure, project team, and I'm going to run that, and it says it's completed. And of course now, as usual, I can recreate it and I can execute it again, and I can drop it again. And then when I try to execute it, of course, it doesn't go. And I create it and execute it, then of course it works. And so on, as we've seen it elsewhere. Good. When you play around with these things, it's always a good habit to make sure you drop the stuff at the end, so you clean up your database again and you don't start collecting all kind of garbage in there, and sooner or later you don't know anymore what you have and you get caught out and say, why is the script not running? And of course you forget that you have the object already. So that's the kind of features you have with stored procedures. Of course there's an alter procedure as well as with all DDL commands. There's a create, alter and a drop, but similar, like I've said with views, I gently forget about the alter because it's no point really. You may just as well drop and create the procedure. Good, and that gives you a wee bit of an idea about stored procedures. In this lesson we want to have a brief look at triggers. Similar to stored procedures, it's a complex subject in its own right and certainly could fill a course on its own. So we're just going to get a glance here what you can do with triggers to give you a bit the idea. Also in means of implementing triggers, it's very similar to stored procedures. So what is the special of a trigger? The idea of a trigger is that on any kind of database activity, like an insert, an update, a delete, in some databases on a select, you can actually trigger another action. An example we're going to use here would be using our person table, which has that created column. And the way we've set up the database, this created column gets populated automatically whenever we insert a record with the current timestamp. Effectively, there's a trigger sitting in the background doing that. Now, in MySQL you can only have one such column. So if we were going to have a column which is a modified column, or we wanted to use this create column to rather be a modified column, so every time a record gets updated we want to change that date, we would need to implement that with a trigger, unless we wanted to do that manually as part of any update. But the whole trick of a trigger, of course, is that these kind of housekeeping activities are done automatically and are not depending on the user of the database to do that properly. So we're going to look at that example, and I've prepared the script for that here. So again, similar as with stored procedures, it has this kind of slightly weird delimiter bracket around it, and then you have here the actual trigger code. So there you have a create trigger this time. Again, that thing gets a name, and I've called that set modified because that's what we're going to do. We set the kind of modified date, so it's technically called created here. And then you have a number of additional parameters. So first of all you have a before or after, then you have the activity insert, update, delete, and you can combine them. So here I do on the update, and then you need to say on which database object, so on which table. So update on person we are going to do here. So every time the person table gets updated, we want to set that created date to the current date as a kind of modified date. And you see you can do this before or after update, and certain things only work in certain context, and for example what I want to do here only works with a before update. That sometimes is a matter of playing around and finding out. The other interesting bit you can see here, of course, is, and that is what triggers do quite commonly, is that you work cross-table. So you do an update on one table and the trigger will actually execute some other query on another table. The classical example for that is a cascading delete. If I was gonna delete a person from the table that still had contact details assigned in our example or projects assigned, I couldn't do that because I would break the relationship. So I first would need to delete the related table data, and then I could delete the person. And to automate that, you can use the cascading delete. So the trigger would actually fall through into the related tables and do the delete there before it deletes the actual record you've been asking to delete. That's a bit more complex, and we're not going to play with that here because that goes a bit beyond the scope and time frame we have here. So we're going to do this kind of simple exercise where we want to set the created column. And you see again we have this for each row begin structure here, and then again we have that actual activity. And on this occasion we simply want to set the created row to now, to the current timestamp. The interesting bit you see here is you get in this trigger something called new, which is your temporary table, which is your new data that you're gonna update into your table. And in these triggers you always get, in MySQL it's called new and old, in other databases it's called inserted, updated, and so on. So here it's called old and new, so you can actually that way grab the data before the update, the insert, or for an insert it obviously doesn't make sense, but before the update, and then in the new you get the data that are just to be updated or to be inserted. That way you can do additional checks and modify data or cancel a activity and so on. So on this occasion I'm just going to say, within these new data that the user has already set, I'm going to set the created to now. And actually that is the exact reason why I need to use a before update, because else I would do an update and after the update I would try to do another update, and that somehow doesn't make sense. So obviously before really the update runs, I change my new record, my records that I want to update, again by adding this created field, and then I actually execute the update. Good, we're gonna see that in action. So first of all, of course, I need to create our trigger. So I'm gonna execute that piece of code. And as every other thing, of course, it goes very quick and it doesn't show a lot. And of course my select still goes as it is, but now if I'm gonna say I'm gonna change a record, for example, take that record 6 of Susan Baker, who doesn't have a birthday, so let's give her a birthday. So update person, set date of birth equals whatever, 1963, 08, or 09 for example. So, and as usual don't forget the where clause, where ID equals, and she is ID 6. So, and you want to see at the moment we have here some date in February 2013, And now when I run that, of course, because it's an update, we don't see anything, but it says it's completed, and we can do our query again. And you see now Susan Baker has set birthday, and it set it to my current date where I'm just recording this lesson. So that is your trigger setup, and that is a very simple, but even that simple as it is, often helpful functionality where you can use triggers for. Of course, as usual, there is a drop for that, which is then called drop trigger, set modified. And that way I can get rid of my trigger again. So just as with all the other DDL statements, I get a create, I get a drop, and again, similar like with stored procedures, I get a alter here, but it is rather useless. So that's a rather brief introduction to triggers, and if that catches your fancy, there is a lot more to look up, and there is a lot more proprietary bits on each database system you may use, what you can do or what you cannot do with triggers.